Welcome, everyone. We'll have some fun today. We're going to have some fun and some application security fundamentals. So we'll begin in just a few minutes. You know me, I have to give everybody 3 or 4 minutes to join because I'm from Greece. And in Greece, we're late for everything. We tell people the wedding's at noon, and that way they get there at maybe 6 o'clock at night when it actually started at 5. So I give everybody a few minutes just to join.
All right. So what I'll do is I'll give everybody my little bit of housekeeping reminders about how things are going to run, and then we'll let Mike get started here. So keep in mind, we set aside 4 hours of today for the content. We'll be, we'll get through what we get through. We might move into another domain. If so, that'll be exciting. If not, then just enjoy application security. So what we're going to do, Mike will cover some content for a period of time, anywhere from 15 to 30 minutes. And then once he finds a natural stopping point, we'll stop and we'll take questions for a bit. And then Mike will get back into the content and find a natural stopping point again, somewhere in that 15, 30-minute range. And then we'll get back to questions, and we'll keep doing that until we get to the end of the day. So there's no specific break point. There's no specific stopping point of where we're going to take a break. It really just all depends on the topic that's being covered at that time. We encourage you to ask questions. We've got the chat box over there for you to ask questions. And we're going to get through all the questions that we're able to. It's possible that we may get too many questions that we're not able to answer all of them. If we get too many questions, I will have to stop so that we can move back to the content and the interest of keeping things moving. But if that does happen, we are keeping track of all the questions in case we happen not to be able to answer them in real time. Hasn't happened yet that we've had to provide some questions outside of the session, but we are keeping track of them just in case that does happen at some point. So don't worry, if a question pops in the chat box, we're copying it and saving it outside the chat box. So that's how we're going to do things. I do want to remind everybody, I always like to say this, especially when we're getting into either some heavy content or some long form content, dense content, whatever you want to call it. You're probably not going to completely grasp it the first time you hear it. It's just like any other type of education, any other type of training, whether it's your US history or world history or math or calculus or geometry or chemistry or biology. The first time I heard geometry, I didn't get it. That's so I had to watch again, read again, take notes, all that stuff. So that's what we encourage you to do with this. That's why we're recording, so that we can send the recording out to you so that you can watch it. You take notes. Take note of a timestamp where, at 30 minutes in, he mentioned this thing. And okay, when I watch the recording, I need to make sure I pay attention again at that 30-minute mark. So watch it, take notes, be involved as it's happening, and then come back, watch it again, take more notes. Come back, watch it again, take more notes. If you need to, look something up outside. But if you look up something up outside, make sure you go to a reputable source. We always prefer reputable sources. So the well-known security vendors. If we're talking networking, we're going to Cisco. If we're don't go to Jim Bob's blog on jimbobsblog.com unless Jim Bob happened to create it. Unless we're talking about McAfee, if he were still around, had his own blog, But yeah, so if you're going to look something up, make sure you use a reputable source. But I always like to make sure people realize, you're going to need to watch something a few times. You're going to need to read something a few times. You're going to need to take notes. Because I see so many people make that mistake of thinking, okay, I'm supposed to grasp it the first time I hear it. Okay, I didn't get that. I'm not going to succeed. No, that's not the case. You're going to hear it. You're going to hear it. You're going to read it. You're going to read it. You're going to hear it, and you'll grasp it. So that's all my housekeeping. I think that's given enough people enough time to get here. And I think Mike is now probably ready to go. Mike, are you ready?
Absolutely.
All right,
So
cool.
let's have some fun and let's talk about some application security. Now, I gave you all a chance to do physical security today, which is probably the most fascinating part of security, but you all said application security, so let's do it. So we're going to talk about implementing controls around software development because let's look at it this way. If our network's secure and we're using encryption, which we'll talk about soon, and we've got strong IAM, most of our security is there. And then all of a sudden, we put an application out there where somebody wrote code that is vulnerable, and then somebody jumps on that server and hops all over through our systems and attacks everything and brings us down. So the code in many cases becomes some of the bigger vulnerabilities that an organization has, especially when anything is placed on the internet where it's accessible by more people. I mean, we do have hackers on the inside, but on the outside on the internet, everything's out there being hacked. So it's all about protecting that. So if we look at software, if it's developed in a secure manner, the software is pretty secure. If it's developed in an insecure manner, the software is not that secure. Let's say you have a building and the building has 8 entrances inside and out on the first floor. That's the way somebody designed the building because they thought it would be cool to have 8 entrances and exits. Now, let's say from a physical security perspective, how do you protect 8 exits? Seriously, how many security people can you put on how many exits at all times in a building like that? It becomes near impossible to protect it unless you go to extraordinary measures. And that's exactly what we're talking about here. If the code that's placed on the internet is bad and it's vulnerable to attack, well, that becomes a soft target. And whatever the soft target is, whatever the weakness in the system is, that's the part that's going to be attacked as a rule in any kind of warfare, cyber warfare or physical warfare. So when it comes to security application development, we have to begin it from day one. That's what they call secure by design. And the first time the code has to be written, it needs to be secure. But how about when it's patched incrementally? That has to be designed as well. So there needs to be some way that developers can do things in a systemic manner to make sure that security is integrated from day one. And that's what we talk about when we say secure by design. And that really means from the beginning, from day one, we have to think about those applications. We have to think about that as a weakness to the system. So how do we harden these applications? So, and we harden them so that if they're not attacked, and that way we can protect the organization, its customers, its people. So that means that software, and we'll talk about various software development life cycles. And I am not a software developer by any stretch of the imagination. I am an architect. So architects don't code, but we will talk about what goes on through these from an overall perspective, because you need to understand what it is that we're actually securing. You don't need to know how to code as a security architect, for example, but you do need to know what it is you're actually securing. That's a different problem. So we need to make sure that the developers that are writing code are doing things that make sense from a security perspective. And we're going to talk about what that is as well. Now, we have to talk a little bit about programming languages. What are they? It's a way for a user to write code that a system understands. So I could talk to you in any language, and if you understand it, and you and I were working together, and I asked you to do it, and you did it, that makes total sense because you and I are communicating in a language. I communicate in English. I communicate in Greek. I do my best in Spanish, but I'm fluent in these two. So I speak 2+ languages. But realistically speaking, it's just a means to talk to the computer. Just like I talk to my cat differently in a different language than I talk to my wife most of the time. The cat understands different things. So that's all we're talking about with programming languages. Now, there are a lot of programming languages that are out there. And you can have multiple ones use at the same time on the same application, especially with microservices. They could be in 10 different languages along the way. Now, as a rule, most software developers prefer the things that are fairly high level. So what does that mean? Most people are not focused on the assembly language or the stuff that talks to the hardware. What do I mean about the stuff that talks with the hardware? You want to put a graphics processor in your computer? The graphics card plugs into that PCIe slot, but your computer's operating system somehow needs to know how to speak to that video card, or that graphics card. So what's happened is there's a driver that's written. So when we talk about low-level programming, we're typically talking about the drivers, the fully programmable ASICs. And these are some specialty programmers because almost no one knows how to do these things. But just keep that in the back of your mind. When you talk about this, you're typically going down that path. Most modern programmers like to program in things that are like Python or C++ or Ruby or Java. And the reason is it's fairly close to the way humans communicate with each other. So it feels normal. And that means development time is shortened. You don't need as many developers to do things. And it enables people to be more free to do more things. So that's why most people like it. It's more there. But interesting, just think about things as a rule. Whenever you only have people that know one side and they don't know the other side, there's usually some opportunity there for people that are focused on the thing that are critically important. You can't figure out a driver to get this computer to hit the operating system. All your AI is gone. Can't figure out a driver to get the card in your firewall to work and actually interact with the operating system on that firewall. Guess what? The firewall crashes and you've got no security. So keep that in the back of your mind. Both are needed. So when software is done, there's a couple of ways that the software could actually be executed in the system and the way it's developed. And we'll talk about what that typically means. We have what's called compiled programming languages. And if you look at something like C or Java or Fortran, what really happens is the developer writes this kind of source code. We'll map it out. And just so you understand what the process is here, bear with me a second. Okay, so if we have this, box, and this box is full of source code, this could be a million lines of code. Now, most systems can't just run the code. For any of you that ever installed an application on side of your computer, as a rule, did you put 4,000 lines of code in there somewhere exactly where it needed to run? And tell your operating system which thing and which library it needed to point to at every single time? Or did you click some executable and it ran? The wizard, if you will. Or whatever it is on the Mac that's the equivalent of that. And that actually put a single file there. It may have put multiple files there, but it had one executable. Excel.exe, something to that effect. So what happens in order to have that, and this is what I want you to understand from a security perspective, is we've got the code, and this could be a trillion lines of code in today's world, but a million lines of code is still a fair amount to think about. And then that goes through the system over here, and this thing is called a compiler. Some days your live whiteboarding is just what it usually is. But okay, so we'll put a compiler here, and I'll explain what this does. So these million lines of source code, they go into this thing called a compiler, and the compiler takes all these lines of code and it exports it out into something. We'll call it Cindy the cat .exe, and you just click it and it just runs. Now, keep this in the back of your mind. To go from this huge number of lines of code, which in today's world is small for an application, into this compiler to a single line, this is a computationally expensive process. So this is the kind of thing where if you're trying to do this on a developer's trying to do this on a slow PC, it could take 30 minutes, 45 minutes, an hour, depending upon how much code it is. Now, a developer that has to compile code every day gets a high, fairly expensive $5,000-$10,000 workstation, and that 30 minutes becomes 3. So you could see how this is where high performance compute might be needed for people that do a lot of code compiling each day. But that's just something or another for you to think about as if you ever become an architect later and think about all the things that go into design on the compute side of how these processes could occur. in cloud native or non-cloud native ways. But that's what's really going on there. So the key to remember in the future is this is it, the Cindy the cat.exe. So I want you to think of this. We had a million lines of code and it's now one thing with a .exe. What's the big concern? If you know, put it in the chat box. What would we be concerned about from an application security perspective to think about if we're the application creators and we distribute this thing in one single executable? If you can go back and take that one thing and turn it back into the million lines of code. If you could do it, Pablo's right. Can it be decompiled? Now, I've created this proprietary application that's worth billions of dollars a year in sales. Can you decompile this and see what I have? And take it, or take parts of it, if you will, and alter it just enough that it passes the law. Can you also find the weaknesses in my code if you can actually see it and decompile it? And say, there's a vulnerability in that system. Or Billy Bob, the goofy programmer, actually left a password in the system that nobody removed along the way. So you don't want this to happen. And that's the key. If it's a .exe, if it's one of these monolithic applications, which is pretty much half of them, and in many cases may go back to being more, you have to think about that. Can it be reverse engineered? So a lot of work needs to be done on these. If an organization is creating these distributable.exe, monolithic applications, how to protect that. So they need to employ what's called code protection strategies. So you can't really use the reverse engineer tools to go find the weaknesses in the code and then figure out how you exploit it. Now, if we've got compiled code, we installed it, right? Now, other environments can enable code to just run. And it just runs on your machine somehow. Well, that somehow means we have to install something to enable that code to run somehow. So I don't know how many of you remembering have to install Java on your computer in order for a certain application to be able to work. That's the reason. Because something like Java needs to run in that Java virtual machine. It needs that kind of runtime module. So if you don't have that Java virtual machine there, the Java code wouldn't actually run. And generally speaking, there are languages, if they're not compiled, they're what's called interpreted. So you speak to that in whatever language it wants. I like Greek, but pick your language, whatever you're writing that code in, Python, R, JavaScript, for example. And basically you distribute the source code, and that's then executed by some code interpreter on their system. For example, to run a Python script, you have to install Python on your system. And that's really what we're talking about, environments here. So we need to think about all those environments. Are they all the same level of security? No. Let's say you have to run somebody else's environment, like the Java virtual machine environment. You've got two issues now. Does anybody see which two code things you need to worry about? There's two problems, not just one. Do you need to worry about your own code security? Yeah, you write bad code, you got a problem. Now, on this Java virtual machine, what happens if that one has some vulnerabilities in it or code problems in it? You're still subject to it because you have to install that on your system. So the key here is there's an implication of this. If you don't have a code interpreter on a server because you don't need Python on that server, and someone wants to execute a Python script on that server and they can't install an application, can they run that script? They can't. Which is something else we'll talk about later, which is don't have more stuff on your system than you need. because everything you have is there. If it's around the 4th of July around here and somebody's got a car full of fireworks in there, probably not as safe to drive around in that car as if it had no fireworks in there and it had sandwiches, for example, or Greek salads. So just think about all those things that go to it. Think about what you can control and think about what you can't control. And if there's other factors you can't control, what do you need to do to secure them? Or not get work in an environment where there's factors you can't control. Now let's talk about what a software library is. And let's kind of map this out because I want it to make sense so you can see the strengths and the weaknesses and the efficiencies, and then again, the risks with this approach. It's not much different than epidemiology, which is what we're actually going to talk about next. So let's talk about what a shared library is first. So let's say we've got 3 programmers, and programmer 1 is Apostolis, and he writes code. Programmer two is Maria, and she's also there. And of course, we have Nikolaus over here. And we have Vigeli over here. So we've got 4 people writing code. Now, when they all write their code, generally speaking, they put the code in a code repository. And in this repository, we'll call it a library of code. So this means, in many cases, as Apostolis puts code in the system, he puts it in the common repository. As Maria writes code and puts it into the system, she puts it in the repository. As Nikolaus writes code and puts it into the system, it goes into the repository. And when Vigeli writes code, it goes into the repository. So far, what are the benefits of this? I want you to think it full through. I want you to get it. Well, if we put all the code in the same repository for every little thing that we did, it could be our own code repository or a public code repository, but let's say it's there. We've got a couple of things going on. One is we've got a single source of all of our information, which is wonderful. But guess what? Now Medi can see Nikolaus's code and then reuse that as part of her next application. So we've got a lot of efficiencies because a lot of developers can share those same libraries and basically not have to rewrite parts of their code. So Maddie can borrow 50% of Nikolaus's code and 25% of Apostolis and only have to write 25% of her own. And then, of course, Apostolis will say that great code MIDI, all right, and take some of that. And it all works out that way. So does everybody see the strength of this? Now, from an epidemiology perspective, which is the study of disease and how it spreads, does anybody see a problem with this? Because it's a security problem too. If you do, put it in the chat box. Okay, so basically, Pablo, basically that. The key is if we've got bad code and everybody uses the bad code, everybody's got that same vulnerability in their system. If there's something bad and they're like a piece of malware in that code, everybody's got it as part of every single application they have. So what do you think about just taking code from a repository without knowing the quality of the code, the source of the code, or the cleanliness of the code, even if you're not a developer? Well, I know medicine, so I wouldn't want my patients reaching into a container of something that may or may not be the right medication and may or may not be the right dose when it came to their things. Now, if I could guarantee that that is this medication, for example, paracetamol if you're in the UK, or acetaminophen and if you're in the US, and I know that each tablet is 500 milligrams, I know how many tablets any patient can get. It doesn't matter. But we need to know what it is that's actually there. So there's going to be implications to this about how the people write the code if they're going to use shared libraries. How do they make sure it's cleaner, certain things that they should do or shouldn't do? So I want you to just think of those implications. Now, when we talk about shared libraries, they can be available in all kinds of things. They can be a commercial product. an internally developed product, but they could also be, what do you call it? Open source that's publicly out there. Open source code can be some of the coolest things in the entire world. The Linux kernel is open source. I mean, seriously, a lot of the world's almost all the world's supercomputers are powered on something that's open source. A lot of care went into that kernel from a lot of smart people. But Billy Bob, who's drunk all the time, made an application and it's open source and public out there, and you can get this person's code. You want to use that code? Not necessarily. And the people aren't getting paid to do the open source thing. It's people that are doing it as a hobby on the side. Some people are doing it because they want their names attached to things because they think it's going to help in their career. So it could be slop or it could be great. So the key is if you're using open source, you need to be able to really evaluate that before you use it. That means someone that actually can look at the code you might actually need. Because we security people aren't going to be those people. So if we use a secured library, our developers need to know exactly where that code came from and test it virginally to make sure there's no weaknesses in it. So shared libraries can be great. They bring strengths, they bring weaknesses. Everything is a trade. Everything I do here is going to make this worse. Everything I do here is going to make this worse. So we have to really think about which ones make sense to the company. Now, some developers write code in what's called an integrated delivery environment. So what is that, realistically speaking? So if we get into one of these environments, we'll map it out. So if the developer just writes code and pops the code here, unless they compile the code, it's not going to run. They can't test the code unless they were to compile it. And then once it's compiled, it takes time for that. So let's think how we can make it better. So instead of just having it as one thing, if we can create this environment here, this integrated environment, and it's just an application that the developer downloads on their system, and on this thing, on this environment, what they can do is they can write their code here in this development environment. They can test the code and make sure the code's okay in this environment. The code can be debugged and look for problems in the code and the way certain things happen. And then when the user is done with it, they can compile the code right inside this application. So a lot of developers use an environment like this with their code, and for good reason. Now, this is where each developer fights over which one of these they should be using. Does it matter? I mean, it matters from a security perspective to make sure that you know what's on your system, so you know which weaknesses are on there. But from a practicality perspective, remember lots of brands of things do the exact same thing, like your AWS, your Azure, your Google. Different names for the things they're doing, but for the most part, they're doing the exact same thing. So keep that in the back of your mind of what these things actually are and how they actually work and why a lot of it's there. So when we actually look at systems like this, we have to be able to look and make sure that we're going to keep the system secure. And there'll be what's called assurance procedures to verify that the security controls for the applications will comply with the policy, which we'll talk a little bit more later. And it's really a formalized process to make sure that the code is tested. And there's typically multiple approaches to this. There's like a common criteria that you can look at software from a perspective to make sure that it's secure. And we have to do this. We have to go through a process to make things secure. But do we think we can ever make it perfectly secure? Do we think we're ever going to be able to build an environment that's not going to get hacked or have a security vulnerability? We can't build it. We can do the best we can. We use a certain number of length keys, and somebody's got 24 NVIDIA RTX 4090s all working together to crack your key. I mean, depending upon the key length that you use, it can be broken sooner, for example. But also understand gear is going to fail too. Services are going to fail at the various providers, and that also will affect things. So that's what we're going to talk about software and hardware controls to a degree. So here's the first kind of security control we want to talk about. It's input validation. So what does this mean? Let's make sure, let's get another slide here. Bear with me. And I'm sure you've seen this in your life, and now you'll know what it is and why these things are actually there. So let's say you're on a web page, and on the web page, there's certain things that you want filled out. And on this web page, you've got something for the name, and you've got something for an email address. You've got something for, say, a phone number. Now, what should you allow the person to put in these fields? And why does it matter? So let's say when it asks for the name, and then you put in the name Cindy the cat. For example, what instead of putting the name in Cindy the cat, you put in some characters that are going to basically crash the server. Once it hits like an SQL environment, the SQL server is our backend, for example, or a relational database. Would that be a problem? So if I let you do things that you shouldn't be able to do, you're more likely to cause problems. Does that make sense? Have you all experienced in this in your life? You're allowed in this section of the airport, but not this section of the airport. They let you do what you were supposed to do, right? Kind of a lot like authorization in the identity authorization and accounting perspective or IAM perspective. So we're going to do the same thing here. And I'll show you what I mean. So going back to what we talked about here, what we drew, for your name, for example, I expect something that looks like a name. Now, am I going to have things like this in someone's name? No, wait, sorry. Must not have protected the shift. Is that going to be somebody's name, realistically speaking? No. So I'm not going to accept that. Now, what if under an email address, I get the same thing? What happened there? And that's it. No at, no domain, no top level domain. So not at Go Cloud Careers and then the top level domain.com. Is that a valid email address? No. So why on earth would I let you push enter and then send that to me? So this is called input validation. And what does it mean? It means that if you tried to put in this, you get rejected. But if you put in this, we allow it because that looks like a valid email address. Now, if we see a name like this, Cindy, middle initial the, and last name Cat, this still looks like it belongs. Although admittedly, I have a problem. I like cats a little bit too much, but that's neither here nor there. So that's what I want you to think of in terms of input validation. It means we need to make sure from a security perspective that you can't just put stuff in there when it says enter your information. Because you don't want to be able to inject bad code that's going to hit that relational database and cause it to crash, what have you. Does that make sense, everyone? So this is one way that we can protect our systems. Now, authentication and session management. Most good applications require you to authenticate before you can access anything, right? You have to prove that you're you. So Cindy tries to lock in. Cindy gets the camera that looks at her face print, which is something she has. And then because she can't really get her to speak, I have another something she has, which is her paw print. So that's two-factor authentication. I use two types of things. Well, technically it's a little off, but call it two-factor authentication. Now, that is a good way to determine who she is and what she's allowed to do. But realize if you don't authenticate before you actually get on the system, how does anybody know what information they could give you or not give you? So that's one of the biggest things we have to think about when the developers release their applications is, did they give you the right permissions? Are they forcing you to be identified before you get into the system? Are they policing what information you can get by the level of access you need as a customer versus an employee? Are you keeping track of who did what? You have to be. So that's part of going into secure systems is thinking about the authentication and the session management. So we have to think about how we can do that. Now, if we've got good applications that go to a good IAM system, and we talked about IAM on the first day with Isaac, the IAM architect, that is a perfectly good system. Because it's much better to use a very good, well-developed identity system in most cases than to try to figure out how to hack your way through it yourself. And the reason architecturally that makes sense is a company that does IAM all day is probably going to do better than you and your 10 people that are going to try to figure that out on your own. Company that does billions of dollars of sales in one thing, I promise you'll be more adept at than a couple of people you have in your garage, for example, that are working on that, a very small team. So that's why you typically, for best practice, want to use something there. So as opposed to trying to figure out a way to connect these on your own. So when it comes to secure session management, there's a couple of things that need to go in there. So if we had this, and unfortunately you will find this that's out there, and this is an absolute disaster. So I'll show you what I mean by this. Let's draw it out. So let's say you have an application server. And then behind that application, you've got a web server. I'm sorry, you've got a database server. And heck, let's pretend it's coming in from the web as well. So you often see a lot of applications that are designed this way. These three-tier applications, you've got your web servers. And your web servers show the front end of what the world sees, for example. And the application servers run your business logic of how and what you're going to do and what you're offering, what have you. And then when there's a transaction, it goes and gets recorded on here. So for example, let's say this is Cindy's website and Cindy the cat is selling cat jewelry. I have no idea. She's a very smart cat, like a little person. She does what she does. So somebody hits the server and they decide that they're going to buy Cindy's cat bracelet. So then she's authenticated, everything checks, so things are run on the application servers, payments are collected, and then the transactions recorded in the database server, and then you get an email back from the system that says you purchased your cat bracelet, whatever that is. So let's talk about this. Where do things get bad? There are times, and I swear you will find it, that people put a password in the code between the web server and the application server that's hard-coded in the systems and another password on between the app server and the data server. A password that's literally in the code. Now, sometimes they take this and they put it in a public code repository like GitHub with the passwords in there, and that is a security nightmare from an application security perspective. And unfortunately, it happens all the time. But how many people like the idea let me know in the chat box of having passwords stored in any one of these servers on how to reach the next server. I hope not a lot of you, because now I hack into the first server, and then somehow I look at the code, and now I have the password for the next server, and now I look at the code, and I'm like, well, I have a password to the next server. This is common. This is a horrible idea, but this is a common. So what we need to do here is several things along the way to make sure these are actually good. And that's what we're going to talk about next. Things to think about. So that's what's called secure session management. So let's go back to this. And let's go back to this environment. Now, let's say instead of doing any of this, we now have tokens between the system. So the web server needs to talk to the application server. A few things happen. First, we encrypt this. And by encrypting it, we do a couple of things. I'll just put a line here so we can call it encryption. And I know when you get to talk a lot about encryption yet, which we will, but so we're starting here with encryption, which of course I spelled incorrectly real time. And that means that no one can see anything that's going on between these two systems. So any of the messages, any kind of communication is here, nobody knows it. The encryption also enables the web server and the app server to know they are who they claim to be, because that's part of the encryption process along the way. And the data will be what's called hashed. So that'll mean that you can prove that the data hasn't changed between these. So what we typically do is want to encrypt the communication traffic here, and we want to use what's called a token system. So the web server wants to interact with the app server. It goes and gets a token from whatever your IAM system is, for example. And then the token is then given to the app server. And then if the token is correct, the app server grants access, and the web server and the app server can speak. Now, the key here is maybe 60 minutes later or 30 minutes later, this token expires. And then in order for this to continue, a new token has to be created. It needs to check with the token system that the token system responds, and then these two systems are now speaking to each other. So we want to use some form of a token system along the way. And by using some form of a token system, we do a lot of things. So first, there's no username and passwords that are ever going to be passed across this. Everything that we do can't be seen along the way, and these tokens are rotated. So let's say a hacker, worst case scenario, was able to get access to a token from here to here one time. Well, if the token changes every half hour, worst case scenario is, and the hacker got the new token at exactly the same time it occurred somehow, or guessed it, they'd only have access to that system for a half an hour before that token timed out, which is a whole lot different than a password that's going to be here and here or there for the next 6 months or 6 years. So that's what I want you to use, another token, which is a token system and goes back every single time. So that's secure session management. We can use some cookies along the way, but I want you to see that, and I want you to see how much that enhances the communication between the two systems along the way. These kind of short-term credentials. Well, let's talk about error handling and logging. So, sorry, just getting over a terrible cold. And let's talk about error handling. So a lot of times, have any of you ever been network engineers or anywhere where you're debugging anything? Or software engineers, for example, well, a lot of times when something's not working, you'll go to a debug and the debug may show you what's broken. For example, your two BGP speakers aren't speaking because their authentication is mismatched, or the autonomous systems are wrong, or the BGP version is wrong, or something like that. So you get a lot of information when you run those debug commands. Now, a developer may need to do that to test the code while they're testing it. But what happens when they're not testing it? Do they want all that extra information to be generated at all time? Mike spoke to Cindy. Cindy spoke to Fred. Fred spoke to Chris, who spoke to Leo, who spoke to Tyron, who spoke to Alonzo. Do I need or want that? No. So the key is, well, sometimes developers turn on error handling, and if they forget to shut off that error handling, guess what? Now all that information is now available to a hacker. So we need to make sure that if there's ever any kind of error messages that are being developed by the developers and any kind of debugs, that needs to be closed down by the time it's actually available. Talk about this for about 2, 3 more minutes, and then we'll take a break and get to questions. So detailed error messages sitting in the code are an absolute disaster. Now, is information necessarily a bad thing? No, it's who has access to the information. Chris and I share all kinds of information. We need to. But I have to tell you, my landscaper doesn't know the information that Chris would know. So the key is where you share that information and where it goes is something else. If we send it to our logging systems, that information is available to us. But if we leave it on the server and open to the public, we've got a problem. Let's stop there and see if it's a good time to take some questions.
All right, so we'll take some questions now. Only got one question so far, so if we've got questions, please put them in the chat box, and we will make sure to address them. First question is where do you go? Is can you use code obfuscation when you compile the code?
Oh, there's definite ways when they compile that code to make it much harder for what do you call it, for the hacker to actually break that down. That is not an area, Steve, that I do know enough about. Now, we will use obfuscation in many other places that I do know about that we will probably talk about through this, but I don't know the exact method that they do that, Steve.
All right. Well, let us know if you've got any questions. I made Mike stop here because he had been talking for about 40 minutes. So I promised a break for questions at least every 30 minutes. So uh, this is your opportunity. We'll take a few seconds to see if anybody's got any other questions so far. And then if not, I'll let Mike get back to the content. And if questions come in, we'll answer them at the next break. So our next question is token system an alternative to MTLS? Are they complementary in securing server to server?
They're complementary because you know, MTLS is more about the encryption between them, but the token is actually how you authenticate the user in addition to the encryption. So it's actually so it's actually complementary. So what's going on here is MTLS is TLS going back and forth. So if, for example, I want to create an encrypted connection between me and Chris is the web server. Normally, what happens is I authenticate the web server, and the web server trusts me as a customer. When we go to MTLS, what's happening is I'm going to look at Chris's certificate, and Chris is going to look at my certificate before it determines that we're going to speak. That is a situation that we want to use wherever we can because it's so good. Now, at the same time, I still need to go and make sure Chris is who claims to be outside of that to make sure that application one and application two. So typically what happens is we've got a token system and the user goes and it hits the token system, requests a token, gets a token, and then gives it to the other side, and the other side verifies that token. So they're complementary, and it's a great question.
Right. Can OAuth implementation be used if redirect URI are not validated?
You know what? Anything can be abused. And what you realistically do is try and do as much as you want, as much as you can. Validate this, validate this, validate this to get as close as possible. But nothing is perfect and nothing is immune. But they are good best practices.
All right. And those are all the questions so far. So I'll let you get back to the content.
Okay.
And if any others come in, we'll address them at the next break. I just had to give everybody that promised break that I offered. So
One second.
let me know when you're ready, Mike.
All right. So let's get back to this. So let's talk about fail open and fail close systems. And I'll show you the difference of between them. So let's say the types of what I mean by this. So I'll give you an example. And this actually, I can't believe it happened in my house with the firewall that I used to use. And here's what ultimately happened. So I had an environment that looked fairly similar to this, where like many people do, where basically they have an internet service provider and they give you a public IP address, and that public IP address sits on a firewall. And this was an industrial grade enterprise firewall. And then this firewall assigns, an IP address for say the subnet. And then the subnet would speak through this firewall. Well, you know, the subnet that I had on my PC, because this acts as my DHCP server one day, is no longer what it's supposed to be. This is on the wrong subnet. And all of a sudden, this would be on the subnet that my ISP's, router would actually use for its inside, versus this subnet that it actually should be. And I checked my internet; it was still working, but I was on the wrong IP address. So then I did a trace route to see where my traffic went, and it didn't go through this firewall. And what happened was when the CPU, whatever broke on the firewall, died, the firewall decided to say, I just don't exist anymore. And it passed all the traffic that was sitting in here over here. Well, it would have, but I had a second firewall just behind it, just in case. But still, I was reassigned something from the other system, not the one I was supposed to be on. And there you go. That was a firewall that failed open. When it died, it enabled traffic to go straight in from ISP to whatever was over here, as opposed to where it was supposed to go. And it was a different firewall. It was a small firewall over here, but it was on a different subnet that you would get from here, the ISP's little mini firewall versus mine. And I was on that subnet, and that's the reason. So that's fail open. Now, fail open is this. So let's put it this way, because I'm going to show you fail close next. So here's a system. This is a fail open. This, you are here, you're trying to get inside. Let's say you're trying to go in. It's any building. So let's say a restaurant. Now the security guard at the restaurant is tired and takes and just disappears, and they don't put another security guard. Now you can just walk in. There's nothing to stop you from just walking in. It failed open, just like my firewall did. That's why I don't use it anymore. Now here's what happens when a fail closed system is, and this is what you use in a high security environment. If, for example, the firewall breaks, it just blocks all traffic, and you get notified that it blocked every last bit of traffic from coming in. Now, you don't get hacked this way. You don't do any business this way, but you don't get hacked that way. So a business always has to make that decision whether they fail open or fail closed. And go back to this. Whether it's a door or a website, fail open. Your firewall is down. You can come right in, but you can still buy stuff off the server. Fail closed. Firewall's down and it blocks everything. Which do you think you need in a high security system? Fail open or fail closed? Pop it in the chat box. Good, fail closed. Wonderful. Now, you had a CEO that was so greedy that she wanted the business to continue to take in revenue, regardless if the firewall's out. What do we security architects design then? Well, first we recommend don't do this, but then what kind of system are we designing that'll make it work even if there's no security? That's going to be fail open. Now, I say this person's probably crazy because they fail open, they get hacked, and then the business's name is destroyed because they intentionally chose that architectural approach for greed versus protecting customer data. But that's the way I want you to think. Every option gives you something, and every option takes something away. So, what's right? So I'm going to talk a little bit about a systems development lifecycle from a security perspective. I am not a security developer. I've never been to a Scrum meeting in my life. I'm an architect, but we'll give you some ideas of what these types of things actually are. So if we look at how the security is developed, we want to make sure, as I mentioned earlier, that from the beginning, uh, security is covered. So, when you look at project management and you look at things, it's like, how do you get things to keep going and to keep going and to keep going? Create the software, use it, get rid of it when you're done, create the new thing. So, how do you get through it? And I want you to think about what happens when you use a standardized model or framework versus when you don't. I like to use my medical example because I spent most of my time in physical medicine and rehab. My wife spent all of her time in internal medicine, cardiology, and as a hospitalist. So she's hardcore real medicine, and I'm dealing with people's musculoskeletal injuries. So one day, she saw me in the office, and I told the person to take off their shoes, get out of their chair, walk. Then I started determining how far their big toe or hallux would move. I checked the range of motion, their ankles, their hips, their knees. And then I came up with an exercise prescription as well as some other things for them and sent them to PT. Now, that was what I did. Now, my wife was methodical. She started at the head, and then she started at the head, eyes, ears, nose, throat, neck. I mean, she was like a machine. Now, one day I decided to work with her in her internal medicine practice because I missed seeing internal medicine patients. I hadn't done it in a while. And I'm starting at the feet. And she's like, what are you doing? I'm like, well, I got to go to the feet and then the ankles. She's like, head to toe. She made me a checklist. Boom, 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 boom. And what was that checklist? Is basically a framework or a model that says, hey, you could do it any way you want, but so you don't forget stuff, do this along the way. It was really great for internal medicine. I still prefer my foot and walking approach for physical medicine and rehab patients, but it was what I needed there, and it helped me so much. So we're going to look at software the same way. We can have everybody doing it their own way, and Joey gets his stuff on time. Maria gets her stuff done 4 weeks ahead of time. Medi gets her things done 8 weeks ahead of time, but, you know, Apostolis is pretty slow, and he comes in 18 months behind. So what are we doing with that along the way? Why can't we all do it the same way and follow the same path, be more secure? So that's what we're going to talk about for right now. So that's the software development lifecycle. And what is it from a software perspective? Well, we have to go from the conceptual definition. What are we trying to do? We're trying to write an AI program that lets me talk to my cat and have conversations with her, because that's really what I want to do. I want an AI that enables me to talk to cats, birds, and dogs, because I love all animals. So if that's the conceptual definition, what are those functional requirements? What do we need to be able to do? What's it going to have to feel like? What's the user going to have to approach it? How are they going to use it? That's the interface. What's it going to feel like? And then we're going to have to determine what kind of controls are going to need to be there for that application itself. And then somebody's going to have to review this along the way and look at it and say, yeah, makes sense. So that's the beginning. That's basically, how do we protect the application from the concept area? Now, somewhere along the line, someone's going to code it. And I want you to think about this way. If I write code, I promise you, I don't know how to code because I'm an architect, but if I were to write code, I promise you there'd be some errors in it. How many of you speak perfect English, even if it's your primary language? Perfect English with no grammatical errors. I don't know many. So when we think about that, no one writes perfect code either. So what that means is if we're going to have somebody do the coding, we're going to have to set up some process to actually check the code. An author of a book is very similar to the developer. They're writing something. Now, do you think the publisher lets you write the book and they just give it to you and they post it out and in all the new books exactly the way you gave it to them? You give them your 250-page manuscript and they say, okay, we're writing it up exactly this way? Or does an editor come back to you and say, this needs to be rewritten, this hook needs to be here, this needs to be done, this to fix the grammar, they rewrite stuff to make it all in the same tone. So, writer editor. So we're going to have something like this along the way in secure coding. We're going to have somebody write it, and we're going to have somebody look and check along the way. Maybe they explain it to you, read the code. Maybe somebody looks at somebody else's shoulders, and we're going to talk about that. But does that make sense? That writing and editing process and not doing it by yourself? You know what happens if I write something? It has no commas in it whatsoever. And commas, semicolons, and colons are all mixed up. My brain doesn't operate that way. It gets other things, but it doesn't operate that way. It can figure out the routing for 50,000 router organization and plan it in my head and see what's going to happen when somebody changes a command. But, my brain just didn't pick up certain things like that. So we all have certain things that we're good at, but that's where they're going to walk through it. Now, along the line, once the software's built, do we think it's going to be secure? Do we think we can't break into it? If you want to test your martial arts, what do? In a polite environment, you find another martial arts to test it with, right? See if yours is effective. And if not, you get training from the better martial artist. Say, mine isn't effective, teach me, or whatever. I don't care. So that's what we're going to do here. Somebody's going to write code, and guess what someone's going to have to do? Test it. And what will these companies have? They will have people with testing tools where they will go and test the code. Test the user experience. See what happens if you use it. Somebody writes an infrastructure as code script, spins up 10,000 virtual machines on a cloud provider to run on whatever their cheapest thing is, to test it at 2 o'clock in the morning, as if they're all users acting at the same time. They're done the test, they close it, they get off the cloud. It's a system test. That's the quality assurance process. And now what happens when the people in sales say, our sales application needs these two features? Ugh. We went through the whole process of making this thing secure in the first place, right? So what's it going to take to change that? How many things are going to be touched along the way if we need to make a change? How do we test the integrity of those changes and make sure we don't have any new bugs or reincorporate any security weaknesses from the past? Does that make sense? Okay, so that's what I want you to think about. So let's talk about what those phases are. The first thing I said was the conceptual definition. What are we trying to get? Now, this is the stakeholder perspective. What do we need? What do we need that application to do? What is it the customers need from that application? What's the conceptual phase sound like to you? Architecture. This is the work of an application architect. And at this point, we're determining what the project's supposed to do. It's supposed to help the sales rep sell more. It's supposed to help the airline buy fuel at a cheaper price. It's supposed to help the bank adapt to risk at a faster rate so they can reprice risk management or whatever in insurance policies. That's what could be what the goal of the application is supposed to do. To detect medical errors and alert nurses and doctors of potential errors before they occur as become a problem. Any of these things could be what we're trying to do. So that's the architecture phase, that conception. So it's not going to be a long document, but it's going to be what we're trying to do. Now, along the conception, we have to think about the security requirements, and I'll explain what that means. If this application has to connect to someone outside of our system, that's a third party, right? No, do we have control over a third party provider stuff? None. They get hacked and we're not careful, we get hacked. So if we know we need to connect with a third party, then we know we need to probably have firewalls and other things along the way. And we have greater degrees of protections that we might need along the way. So we have to think about that again. Again, that's architecture perspective. That's why the application architects often work with the security architects on this kind of component. And then we start thinking about functional requirements. This is what we're trying to build. And listing specific things, who needs to be interoperable with who, what kind of components are going to meet the needs of these things. So when we know what needs to be done and who needs to speak to whom and how that kind of thing needs to work for the business, and the application architect is work done, is what happens next? They go to the developers, and the developers build whatever this is supposed to be. So we can think of things about what the inputs might be. For example, it's a sales website. They want your name, right? Your email address, potentially your credit card numbers, whatever's necessary, whether that be the expiration date, that 3 other digit thing that could be in the back of your credit card, something like that. Now, in that application, do I want to let you do things that you're not supposed to do? No. If I want you to be able to buy something, do I want to make it real easy for you to do it? Do I want to take you through 50 steps and 50 different logins to 10 different companies? So we need to think about that on the functional perspective. If it's an e-commerce website, how do we make it easier for the person to buy without mitigating security? So that's where we typically think about it. And if it's an output that we're dealing with, what do we do with that data? How do we put it? Where do we store it? What kind of privacy, for example, does that data need? So think about it that way. So that's when we kind of get to this control specifications where we have to prioritize and design security controls around what the application is going to be based upon who the application needs to talk to and what the application needs to do. Okay, this is no different than real life. If I've got a person walking through the building, I need to let them know where in the building they're going to be allowed to go. Now, if I know where the person's able to wander around in the building, does that give me more security things I may or may not have to address along the way? If you're in this side of the building, you have access to this, and maybe I need to secure that other this much further. So I hope this makes sense. We think about data confidentiality here. What kind of encryption is going to protect data the way we might need? How we audit the things. How do I know what the user did when they were on our systems? How do we track it? How available does the application need to be? We need an application that's there that's life-saving, like, for example, a 911 system to be able to dial 911 and a 999 system in the UK to dial for emergency services, for example. That needs to work. That is a very different level of requirements. You pop that in 2 or 3 different clouds, and that way when you have outages, nobody cares, and you can still get get a paramedic or a firefighter when you need one. So if we think about that. So these are the kind of things we need to determine from control specifications how we're going to secure it. Now, one of the things that will drive you nuts with an architectural review board if you're an architect, but one of the things that you'll also to appreciate is the architectural review board. And here's why you'll love to appreciate it. You have an idea and 50 people look at the idea to see what the idea's impact on their systems will be and determine if it's safe. How much does that reduce the risk on you? 50 people are checking what I'm doing. Now, that's the good side of the architectural review board. The bad side of the architectural review board is you got 50 people that can slow you down when you need to move quickly. It's trade. Like every other trade-off, it's about balancing trade-offs. But same thing with the design review. That review is going to have to be a lot of things. So there's a design that we think we have, that we architects created based upon what the client told us. We present it back to the stakeholders. This is going to meet your needs. They go back. So that's typically what we're talking about design reviews. A design review can be on the architecture side. A design review can be on the code side, but think about that. But how do we review it? We have to get the user to see if it works when they want to try to use it, or we've got to get the user to say, yes, your design or your architecture is good. Either way, we have to go through these design reviews. Once we really did that before, what did we really talk about? What the thing we needed to do, what the goals were, what kind of requirements it had, how we're going to secure it. Now, we architects just walked out of the equation. We are cloud architects and security architects, and now we bring in the engineers. And that's when the developers begin to code. Because now we've already designed what they're going to build, and we've already gotten the stakeholders to say, yes, this is what I want. Now it's time to get it done. And that's where we deliver it to the developers, and they will start coding this. Now, if we think about it, let's talk about ways that we can make sure the code's going to be secure along the way. So one of the things is what's called the code review. And that's that kind of editing process that I talked about, like the writer does. You turn it in and somebody edits it, checks it along the way. Now, there's lots of different types of code reviews that people do, but generally speaking, in a code review, someone looks at your code. It's like an editor would do these things. Now, not only does someone have to look at the code, someone has to test this. And there's lots of people that have a QA background that do this kind of testing, and they performance test it, they test code, they try to break things, they look for various attacks to see if everything's are good. And they do that on new code. Now, they also do another kind of testing, which is called regression testing. So here's what that is. So have you ever noticed that at one point your computer has a bug? And then you get an update and all of a sudden you don't have that bug. But on that new update, something that was a bug before that you didn't have in the past came back. Well, what's going on is sometimes in the process of fixing something, they reintroduce an old bug. So when these things are tested, not only do they have to test for new bugs, the QA people, but they have to test to make sure the old bugs weren't reintroduced by using shared code libraries or something else. So think about that. So again, all this stuff goes through those developers and the engineers and QA that are actually writing this stuff. And then there's testing. Now, there's typically functional testing, which makes sure that the software can do what it's supposed to. And then there's some user acceptance testing, which is where the developers give the software to the users and say, here we created what the architects designed, and the users say, this works for me or this doesn't work for me. And in many organizations, the architects design something, the developers design something that's sort of what the architects designed, but not exactly. It's a little off. They give it to the people, they look at it and they're like, no, I need this fixed and that fixed, and it goes through the process. So it's like building a house. An architect designs it and then the builder builds it, and then you actually look at what they built and you went, yeah, this is not so great. Let's just fix this. We'll change the carpets. We'll put in a different set of floor. We'll paint it or whatever, and then you move on. I just do what I'm told when it comes to moving, and everything is there, and we just do what I'm told that we need to upgrade, and it just sort of works. But there is that. So, and then again, I talked about it earlier, that change management process, but we constantly have to figure out what changes are. Constantly. We consistently have to think about how the systems operates, what's changing from a process perspective. If orders processing changes, we have to think about it. If we're storing our things somewhere else, we need to think about it. So everything impacts everything else. So that really gets into the change management kind of process, which is this. I want to make a change. When do I make the change? I mean, seriously, when do you make the change? What if the change takes 10 minutes and can bring the systems down for 10 minutes? Do you do that to an investment bank when the market opens at 9:30 a.m.? Is that when you take the bank systems online during one of the busiest parts of trading during the day? You take that system down when the UK markets are closed, when the US markets are closed, and right before the Japan markets open, in a tiny little window in the middle of the night or wherever you can find it, where the business is going to lose as least amount of money as possible to make that change. And that's what you're typically looking to do, finding that window. So first is when you can make the change, and then who's going to make the change. Do you want the people making the change, the people that aren't really sure how this stuff works and fits together, only how to put a couple of commands in the system? You want them making a change at 3 o'clock in the morning because you don't want to wake up and be bothered? Or do you want someone that can truly understand the impact of I made a change and then something broke and how do we fix it fast? Or how do we revert back to what we had before? So then there's that. And any changes, we have to know who can do it. And that could mean every different part of the business saying yes, which means if you want to schedule one change on a router, it could take you 6 weeks to figure out when it could be done. This time, nobody's doing this, nobody's doing this, nobody's doing this. In a truly high availability environment. I know most people don't work in these, but that's all I've ever worked in. So it becomes fairly complicated in these environments to do these kinds of things. So while I talked about software development life cycles, understand there are several approaches. For example, like if you're familiar with anything related to agile or project management, you're familiar with those types of approach. So, the oldest approach to software development was what you call the waterfall model. And that's a very old but very straightforward approach where basically in the development process, everything kind of flows downhill like a waterfall. So you may have a phase like the requirements phase and an analysis phase in this model, and a system design phase, and an implementation phase, and a testing phase, and a deployment phase, and a maintenance phase. And each phase is completed before the next phase begins, like a waterfall. You do this before you can do this, kind of like a karate class. In this white belt, you're allowed to learn these things, but now you're in the yellow belt program and now you can learn this. Like a waterfall, they open up new things as you have the capabilities to do new things. That's the waterfall approach. Now, if you think about it, there's a lot of good things with this, right? Very structured, very simple. You complete step one before you go to complete step two. Hmm. Can you see how that makes it better in some ways and makes it worse in other ways? Can't go to step two until you've completed step one. But what if you could do step one and step two concurrently or at the same time? Might that be more efficient? Sometimes you can, sometimes you can't, depending upon what you're doing and where you're doing it. So there's other models we may talk about. So there's a concept to the agile model, and that's more on process adaptability. So agile methodologies tend to encourage more flexibility in the way things are done. And it's more about collaboration through teams. So when we look at that, that's one approach that could work. There's another type of agile methodology, which this is as far as I can go and talk about Scrum because I've never been part of anything Scrum in my life. But that's another type of agile methodology. And it's typically used for managing software development projects. And the goal with Scrum is typically to produce something fairly quick with some kind of sprint, 2 weeks, 4 weeks for something. And that's an approach that's typically used. So I'm not saying it really matters which approach. Every one of these models is going to have their strengths. All of them. So it's about the business finding what's more right for them to really think about. DevOps is another model. Realistically speaking, it's not necessarily a standalone software development model, but it complements any of these things and it kind of works fairly similarly. And what is DevOps really looking at? It's looking for short, more manageable iterations by doing infrastructure changes at the same time as you deal with application changes. It's designed to be quick, fast changes. Okay, fast changes. We're constantly changing things. What does anybody think about quality that way? I've got a power plant that has to generate power 24 hours a day, 7 days a week, 365 days a year. It's in Newfoundland. It is cold and it's the wintertime, and I need heat for my houses, for example, that aren't gas powered. Can that power system go down? People need their heat. Can't go down. So, do we want DevOps here where we're changing code every 3 days to add an extra feature? Or do we want perfect code that's been tested and done very slowly and very carefully? And that's what I want you to gain from this is we're talking about all the options, but they're just options. They're just choices. The choices are always dependent upon the need. And that's what I want you to think of as we start talking about these things, because there's a million and one of these approaches. Give me a minute. I'm trying to. So let's talk a little bit about what goes into change management. That's a pretty critical governance, control, and security. You may hear it as a control management as well. Now, if we've got high security systems, we need to manage what goes on with change from all kinds of perspective. And this is a fairly structured process. So what goes on to it? The first thing that we have to do is we have to request some kind of control for the change. How's that going to be done? So we have to, typically speaking, if we're going to want to change something, talk about what we want to change and why we want to change it. I want to update the code or the firmware on this router. Why do you want to update the firmware on this router? Because it's got a pretty bad security vulnerability, which if it's executed could take down our entire network. Okay, that sounds like a good reason. Did you test the new code in the sandbox to see if that doesn't have the vulnerability? Yeah, we have. Maybe that's worth it. So the key is, now here we go. We want to update the code. Why do you want to update the code? Well, these devices we have weaknesses in them. Aren't we going to be replacing those devices in a week? Well, yeah, but we've got a vulnerability. How big is the vulnerability? And what's the risk of actually making these changes? All right, for the 1 week, it's probably too risky to make the change. Just let it go for this change and make the change for another one that's critical. So I want you to think about that next. So that's really what's going to be there that needs to occur. So whether that's for a release, but someone has to look at that and someone has to assess the impact of that change. That's typically your architect teams and any kind of architectural review board. Now with software, they have to do what's called release control. Now, have you ever worked on a group project or try to write a document with someone and they send you the old document instead of the new one, they send you the second most recent document instead of the new one? And they save it with 18 names, and by the time you're done, you don't know which document is the new one, which document is the incorrect one, and which is which. We've all seen it, right? Now imagine trying to run your software business like that and not knowing which system you actually ran and which thing had which features and which thing had which code. So that's called release control. In that way, everything's got a number, a structure, and a process so somebody can figure out what's doing, when it's doing, how it's released, why it's released, and then which release is which. Now, if we think about how do we make it scale, anything at scale, from a security perspective, from an application perspective, let's say we've got a mass application that has to be deployed in a large environment. Well, we've got a couple ways to do it. One is I let you install it yourself, and then I have a corporate wiki that tells you all the settings that I want you to modify along the way. How effective do you think that would be across 80,000 people? or across 100,000 systems? Not very, because what would happen? Some people would do it right, some people would do it wrong. We'd have all kinds of problems. So when we're dealing with something, we typically need some kind of software configure management system that gets there along the way. They can actually look at various software versions that were used and how they were used and what have you to make sure they're on the right one. And typically it involves sending these systems to like a manager system. Now, other things that can occur is some kind of configuration control along the way to make sure that everybody's on the same version, if you wished, and how updates are there. And if you work for a large company, you may notice that your updates might pop in and say you have to install these things, for example, and something's checking your computer to tell you that you could, or you can't get on until you update this. That's kind of that kind of configuration control and action, kind of keeping you from not using what they want, getting on with weaknesses. Now, along the way, someone's got to track what was done. Who made what change where? Hope you guys can think of why that would be important. Maybe one of your developers you found out was fairly incompetent and did a whole bunch of things that were usually wrong. And you could look at where their code commits were. If you just tended to know things were breaking, now you should obviously look for everything. But if it could be one of 10 problems, start there because it's most likely with a known problem, for example. So when you've got accounting, you can start looking at things along the way. Now, along the way, companies typically need to audit what's out there of these software systems that are out there. So configuration type audits along the way. I'll briefly discuss what is DevOps, but I'm an architect, not a DevOps engineer, but something we should probably talk about because it's part of software development life cycles. So DevOps is really integrating or the goal of it is to integrate the operations and the software development at the same time. So what is operations? Operations is running the systems, keeping things up and running and maintained. Business operations, keeping that business up and going all the time, how the business does this thing. So uh, there's always been a side of the development side that maybe compiles the code, for example, another side that tests the code, another side that does all these things along the way. And then there were developers doing one thing. So the developers would hand it off to another team and another one would do it. Now, in some ways, having two sets of teams is an advantage. It gives you a lot of opportunities to check for extra quality along the way, but it also adds a lot of time and potential inefficiency. So the concept behind DevOps is by, doing things in a somewhat automated way. You write the code gets tested along the way. Potentially you can compile it along the way and do a few other things or use systems that can deploy it or make it easier. It puts the business in an environment where they can make rapid changes. Again, rapid changes are great for making new features. If I'm developing a video game, new features are great. If I have a power plant or a phone company, new features may not be so great. Stability is more important than the velocity of features. So always think about that from a security perspective. But DevOps is designed to do things faster. And it uses this concept of continuous integration where basically code and code changes are all placed into in a central repository, and it gets verified by code and tech checks along the way, and then it gets billed by automated build systems where it's compiling the code, and then it gets tested along the way too. It's kind of one process, and in many cases use tools to do this and automation to do it. So it greatly accelerates software development, and it greatly reduces the cost of the software development and the software operations people. So this is why companies are moving towards this. Now, it enables that kind of continuous delivery of validated code changes fairly quickly. It reduces time to market, it minimizes deployment risk, and enhances agility. So if you think about it, I don't know how many of you remember the days where you would get a patch for your system. For example, Windows would make a service pack once every year and you would install it and that would be your security things, but they were well tested. And then there was 3 months later, there was an update. It was a big update. You did it. Now I'm on Mac because they're using DevOps for all these things. Every week it wants to update my Microsoft Word, my Microsoft PowerPoint, my Slack. I mean, it's like every week. And that's because every week they're fixing things each time. Now, telling me it's bug fixes, but nothing else kind of really doesn't make me feel good about what's being changed. But, that's it. Bug fixes, not what kind of bug, whether it's going to help me or not. But that's the key and that's the goal here. And you see it and you experience it every day, even if you're not a software developer. The key here was continuous testing. Now, the key here is if I've got one of the options to test software is automated tools. So a lot of people use Grammarly to check their writing. It uses AI and it looks at your writing and says, this is pretty good, but make this fix. Well, continuous testing in these tools are fairly similar like that. It will look at your system. It may or may not use AI depending upon how they're done. And then we'll look at your code and test your code. And it can be tested for security weaknesses and code vulnerabilities as well as code quality to a degree, automatically by a machine. Machines are cheap, right? So it is there. Now, machines make mistakes too, just like software developers make mistakes. Anything can make a mistake. But the key to think is that's that concept of continuous testing that goes on. It's tested, automated in a very fast way. You release. If there's a problem, you fix it, you test out, and you release it. So the goal here is to detect bugs quickly and fix them quickly and release new things quickly. But again, that could have an impact on your security. But it's continuously looking at it, you're continuously tuning it, and then it potentially can auto deploy it for you, all in an automated manner, enabling this frequently releases and reducing the number of software developers you need in your environment. So that's why these companies love that DevOps type environment and those types of engineers. And you can consistently monitor it. And you're constantly looking for vulnerabilities, weaknesses along the way. And if you are, you find them fast. So that's really what's going on with DevOps. Now, another thing to talk about with regards to application security are APIs. And what are APIs? So if we map them out, what was really going on here, and we have to think about this. An API or an application programming interface is enable you to connect to something. So here we go. We've got this API over here. And I have honestly no idea why, but Cindy, I don't know how she did it. Cindy started a cat food business. Somehow she got my 8K cameras and she got all the studio equipment here and all the microphones and she started out as a social media star and now she's got 10 million followers and she's got a food business. So she is a wholesaler to everybody else that's actually out there in the food business. And after this, we'll take a bit of a break. So what I mean by this is because she's the biggest wholesaler out there in the cat food world. So she's the cat queen. She's the big distributor of cat food. So along the way, Chris's cat Sunny decides that she wants to start selling cat food on the side because she wants more shrimp and lobster and sashimi tuna. So she wants to get into the business like Cindy. So Sunny wants to connect to it. Now I have this deep desire to get an orange Maine Coon. So Cindy hasn't agreed to this, but let's say we call it Spike. The Maine Coon wants to connect and they all want to get into Cindy's business. So they connect via this API. And that enables everybody the same language that they can speak to connect to Cindy in a mostly secure manner. So the key to remember is this becomes the interface for other people to connect. So what does that mean? It means we need to protect this along the way. And that's what that means from a perspective of an API. So that's what we'll start with. What we'll do is we'll take a few minutes of a break, and then we'll talk a lot more or a little more about APIs. We'll talk a little bit about API security and what goes along with that to a degree as well. So let me stop, take some questions if there are, and then we'll get back to the content.
All right. So this is just me making Mike give us our obligatory break for questions. So let's see what kind of questions we've got. Uh, so one of the questions from a little while ago was, is fail open meaning no fail over FW? I'm guessing firewall.
So in this case, I only had a single firewall and then a second layer of firewalls as opposed to two in a high availability configuration. But any firewall can fail open or fail closed, and some are known to intentionally fail closed. Now, if I had two of them there with, say, an HSRP or a VRRP type environment where my systems were pointed to that virtual gateway and one of the firewalls failed, that going to the other firewall would be okay because that would fail closed. The firewall wouldn't act, and then the other protocol, like a VRRP, would take over as a primary, and we'd go out that firewall for our users. So that would, in that environment, that's just a high availability configuration. But fail open can literally mean you could have two of them in if they were synchronized. But anytime where anything fails open. And that can happen with the application the way it's developed. It can happen with a firewall that does that. It's just an architectural choice. And it could be for the code, it could be for the firewall, and it can even be how you run the front gate of a business. If the receptionist is not there and there's nobody to give out the badges to go through the security at the first side of the building, nobody can get in. That's fail closed. Fail open is used to allow people to just walk in. So these concepts are used everywhere.
All right. Next one. All right. Can I say that the software development life cycle applies the CIA triad in code development in addition to other phases of software development?
So I think what you really have to think of, everything we're trying to do architecturally is to get to that CIA triad, that confidentiality, integrity of availability. So what do I mean by that? So if I can break into your network and close your network down, you're not available. That would be network security. If your code is so sloppy that a hacker can break into your system, that's an application security, which will do two things. It will potentially break the systems, or it could break the integrity of the system along the way, or that application could give away confidential information. So again, that's why we get into application security. Now, if you can get on my systems and do things on my systems that can hurt me, again, that is another system. So that's an IAM part going to the IAM. So that's generally the thing that I want you to think about. Everything we're going to do. Encryption is to maintain confidentiality, but it's also of the information that we actually have. But encryption can also promote availability because I can make sure that if two devices that aren't supposed to connect don't connect to each other, I can prevent, say, bad routes from coming in, which also can take my network down. So I think I would look at it the exact opposite way you saw it. And because I love the way you drew the connection. Everything we do is to get to confidentiality, integrity, and availability information. That's the big three goals that we're working for. And each thing that we talk about is to get to those goals. I really like that question.
All right. So next one, is legacy software generally more of a concern than contemporary or modern software that's developed with up-to-date tools and procedures? Can you think of
Not
an
necessarily.
example?
Not really. So, I mean, here's the thing. If it's created and it's great, just because it's old, it doesn't mean it's more vulnerable. I mean, it doesn't. So, what is the industry standard broadcasting microphone? It's just Shure SM7B. And you know where they were designed and invented? 1978. It's not, and they're still being considered one of the best voice microphones in the world. And the prices you pay for it too. But that's the key to remember. It doesn't have to be new. Some things are designed that are highly secure, that are old. Other things that are created now are all kinds of buggy and full of bloated code and full of vulnerabilities. So I wouldn't necessarily look at its age per se. I would look at how it was created, what it was designed to do, how it was designed inherently in the first place. Because there are some systems that are fairly secure, they're old. And there are some other systems out there, like I wouldn't be wanting to run on, say, Microsoft Windows XP. That would be pretty scary. But, there are certain control systems that have been done on a BSD Unix that were locked down from the beginning.
I mean, the Voyager space satellite's still running off of Fortran. So,
Yep.
and it's still getting back to us somehow.
Yep.
All right. Let's next one. In your example with a database server, an app server, and a web server, how would you start a risk analysis? Which are for your important elements of preventing such risk? What tools would you use for a risk analysis?
The risk tools that I would use for risk analysis are your Noodle and Microsoft Excel and potentially a financial calculator. But that is it. Those are the only tools you will ever use. But to do this, and I don't have a lot of time because this is actually a topic of itself that we could potentially talk about for a whole day. But the first part of it is being able to identify the organization's assets. Now, who's going to give you that? The company's executives. Because you may not even know the company's assets as a regular employee unless you're working on that new multi-billion-dollar new special secret formula. Maybe 50 people in the company know about it and no one else does except for some select investors under an NDA. So different people will always have a different level of knowledge and information and things that we actually have to secure. So we have to think about what's actually going into that along the way. And I forget what the question was again. I know I got to half of it, Chris. What was the rest of it?
They were asking how to do a risk analysis on a
Oh,
three-tier architecture.
oh, so the risk analysis isn't on the three-tier architecture. The risk assessment is on what is on that business itself. And what I mean by that is, so if that architecture were to get hacked somehow, what is the impact of someone using that to get into the system and stealing the secret formula for a new drug for a pharmaceutical company or the secret formula for the next GPU? So first you have to figure out what the business assets are. Then you have to analyze the risks of those assets. Then you have to analyze what goes into protecting those various assets and what it costs and what your options are. So do I mitigate the risk? Or do I say the risk is too expensive to mitigate and do I transfer the risk to someone else? So then the process becomes is evaluating the risks, prioritizing the risk, and then determining what those can be that we can do. And that's really going to be the process to determine it and then rank the risk by financial impact to the business. But it's not just that. And then we would look at it now, and then the other components are looking what we'd have to secure with the website, how we would make that demilitarized zone, what we're doing, what those potential risks are to the applications and how we would mitigate them. But it's not about the website we're trying to secure. And that's actually a good question. And that's where people miss architecture versus, say, engineering. Engineering would focus on the website. So engineering isn't doing that risk assessment. Engineering is doing a vulnerability assessment where they look at the weaknesses and figure out how the hackers would actually get in. That's more the assessment of the tech. The architects are doing more the vulnerability, the more financial risk assessments where we're looking at that business itself. And what happens if a business process is compromised? Or what happens if this is compromised? That's the key. And there's a lot that goes into that, but it's a great question. That's
All
why
right,
we
our
have the
next
security
question
architect.
is, I'm just wondering, this is following up on the fell open thing. I'm just wondering if fell open and fell close configurations happen in AWS or Azure, since the firewalls are mostly managed by the platforms. This may be a naive question, but I am naively thinking this implementation will be more applicable if you have an on-prem infrastructure.
Nope. This is applicable everywhere. You most likely won't be using those cloud provider native firewalls because they are very weak in comparison of what they can do compared to the industrial firewalls. So even when you're on the cloud, I don't know. I can't think of clients where I could use like AWS WAF where I wouldn't want to use, say, a Palo Alto WAF, or I can't see any environment where I wouldn't want to use a next generation firewall from a Cisco, a Palo Alto, or a Fortinet. The risks of what are just too great because the cloud provider systems lack behavioral anomaly detection. So they lack really heavy duty security. But it matters, and none of this changes because, what's the difference between a public cloud and a private cloud? Nothing at all. Either you manage it or they management, but it's theirs is not more inherently secure or in any way, shape, or form.
All right. What mitigation strategies would you put in place to help prevent a cache poisoning attack?
A lot. And what I mean by a lot is I'd have things in my DMZ. I'd have different ACLs determining everywhere who could speak to whom. I would have an encryption strategy making sure everything's speaking to whom. And it's really going to take a complete and total strategy. So this is going to affect every domain that we talk about. So today we're talking about this. Physical security will have a component on it. And I love the question, but it's going to take everything we're discussing in this entire environment would be necessary to actually do that and then some. So the key to remember is you can be attacked in a lot of different ways. So if you can break in, then you can do whatever you want. If the network security is weak, you'll be able to do a cache poison. If your IAM systems are weak, you could potentially do a cache poisoning. So it takes everything. And we'll keep covering components of that everything that are here. If you can plug into the network when you shouldn't be able to plug into the network because your physical security is bad, you can basically send bad information to the cache and poison it. So that's why it's going to take this multi-pronged, this full architectural approach of everything. And that's a really great question because what the website, what's it going to take? It's going to take everything. The remote access, what's it going to take? It's going to take the same everything. It's just in different parts that do different things. And there's certain best practices for various components.
All right. And this one will be our last one, and we'll let Mike get back to the content. What is the security implication of allowing cookies in a website?
Well, it depends who we're actually referring to. So allowing you to receive cookies enables people to track you, what you do, what your actions are, and then send targeted advertisements to you and potentially use various components of privacy. There's that one side of it. Now, the component of the good and the bad is, every time you have a cookie that has various information on something. So most organizations are pretty good to make sure that your cookies are not a danger to them. They do what's necessary to protect that along the way. And that's application security is not my area of expertise, but they can protect against that. So the question is what happens if you don't allow cookies? Well, then it becomes very hard to track your users. You might not, your users may have to log in 4 or 5 different times into your website versus a single time to access a certain things. The user experience could get pretty bad. So what we have to do is we have to weigh do I make it easy for my user to buy from me? Which is typically the business's biggest goal unless they've got extraordinary security, or do we worry about that? So most organizations are accepting cookies and they've found a way that it's worth the risk. But everything we do, everything we collect, everything we look at always becomes a bottleneck and could potentially become something. So we have to look at it from a case by case basis. For most businesses, the ability to actually sell something, which means they can run their business and pay their staff, is probably more important than the risk of a cookie. But yeah.
All right. Well, you are free to get back to the content.
Okay. And these are really great questions. I really love this. So if we think and go back to the APIs or application programming interfaces that we were talking about before, what are we really trying to do? We're trying to do a lot of things along the way with them, or at least the developers are. So first, This API makes it easy, which means Sunny and Spike and we had this really great cat in Philadelphia. His name was Rambo. We actually had three Rambos. We really loved this cat, all three of them. But anyway, so we had these cats named Rambo. And this enables all three of them to easily figure out. Now, if there was not an API, here's what would have to happen. Sunny and Cindy would have to come up with an arranged way to communicate with each other and then somehow and write code based upon their arranged way. Spike and Cindy would have to arrange it ahead of time. They'd have to write their own code. Cindy would have to open various things on her systems to allow Sunny to speak, to allow Spike to speak. Rambo, same thing. Rambo would have to start writing code here. So if we think about this, let's talk about the difference. Now, it's going to be really expensive if every cat that wants to work for Cindy and her business has to start writing code or complicated code to get to her. And it's going to really slow everything down if Cindy's IT staff, which effectively is me, but that's whatever it is. So if Cindy's IT staff here decide that they have to start writing code every single time and it's different code to speak to everybody along the way, this is a problem. So that's why we came up with the concept of an API. Now, if we think about the API, let's think about the practices here. Now, if we go to this API, let's think about security. What if this API enables me to get access to 100% of Cindy's things on her servers? Because it's wide open. Here, just connect to me and you get access to everything. Do we think Cindy's cat food business is going to do real well this way? No. Cindy will be hacked this way. She's way too smart for something like this. So what is she going to do with her APIs? Well, she's going to determine ahead of time, what do I need to expose? And what needs to connect internally? So maybe they only open a single IP port that this thing can connect to. And then maybe it only connects to one service that's sitting inside one of these servers that's sitting along the way. One action. So what did we do to this API? We minimize the information we exposed. So we can only get a certain thing. And along the way, we made sure we made it easy for you to connect to us in a very clear manner. Now, we protected our system. So what happens if you break into the API? If you hack through it, you're now on my system. So we have to do several things here along the way. First, we can't just let anybody use this API, right? So put in the chat box. How do I determine who you are and what you're allowed to connect to? I use IAM, right? So clearly we need to use IAM to determine that, the cat that's connecting to Cindy's thing is who she claims to be. And at the same time, we don't give her access to more than she needs. So we're using IAM and the principle of least privilege here. Now, if this system is connecting, for example, at, let's say this is listening, this system, just for argument's sake, let's just say it was 192.168.11.5/24, private IP address, for example. And I know that this IP address is going to only accept TCP at port 1, 2, 3, 4, 5, whatever. So look at that. I can say only this user is allowed to access this at TCP port 1, 2, 3, 4, 5. Hmm. What kind of things can do that? What two devices do I have in every data center, in every cloud that enables me to protect a subnet with some form of thing like an access list or a rule that says you can go from here to here and no more? Every router can do it, every firewall can do it, and every single cloud provider can do it with, say, an ACO. So, how do we protect this? And this is why it all goes together. We only let certain IP addresses connect to it. And we do these things. You could put a firewall over here as well to protect this API. Now, I want you to think about something else. Okay, so Cindy runs this food business. And as it turns out, I don't know why, but there's a golden retriever in the neighborhood, this beautiful golden retriever, and her friend, who's a yellow lab, really nice two dogs. And they find out that they're not happy that Cindy the cat is making all the money and they want to open a pet food store too. So along the way, both golden retrievers and the yellow lab, they're nice dogs, but they are not here to help Cindy along the way. And they decide that what they're going to do is they are going to flood, and I love dogs too, but and these dogs are going to flood this API with so much traffic that it's DDoSed and the API can't work anymore. This is another kind of thing that can happen. So what can I do with on my private clouds along the way? I can rate limit, and you can still do this to degrees on APIs with API gateways as well, but I can rate limit and I can say that anybody is only allowed to send a small amount of traffic, which that's called rate limiting. It's also called traffic shaping. So this way, if the dogs figured out a great plan of a DDoS attack by sending 100 gigs of traffic, uh, the dogs are rate limited to 1 gigabit per second, and they're not, or 100 megabit per second, or 1 megabit per second. They're not allowed to do any harm to Cindy. These dogs are great, and they're just playing kind of for fun. But the key to remember is that's the key is we can rate limit this too. Now, if I have an IDS IPS system that's sitting between the dogs and the API, and the IDS IPS system says, "Whoa, there's something bad here. Stop everything." I can do that. And that's one of the reasons that we don't typically use the cloud providers' firewalls is they can't do that. But with the modern firewall, if we chose it here, the firewall can sit there and the AI can be looking and say, there's a pattern of behavior coming from these dogs and it just doesn't feel right. So let's just block them. It looks like they have ill intentions. So that's what we're typically talking about. How do you protect an API? Now, the reason, because the last question was so good, that last question that came in that said, how do you protect something? And I loved that question. And that's why I said it takes a little bit of everything. So along the way, if the dogs want to communicate to this API over a network, and let's say these are good dogs and they want to be friends. So now these are dogs who want to be friends. What do they want to be? They want to be an affiliate. So these are happy, friendly dogs. We love dogs around here too. So the dogs want to connect. Now, if I'm running encryption between the dog and the API, the dogs and the API, it means that nobody that's trying to spy in the neighborhood can kind of see what messages are being sent. And it enables the dog to prove to Cindy's API that they are who they claim to be. And that nobody changed the message. So when the dogs want to buy 40 pounds of dog food, uh, that somehow along the line it doesn't get changed to 4 pounds of dog food, and the dogs get upset that they're going to be hungry in a few days. So that's the key that goes into this. It's going to take everything. And because APIs are so important, we're going to combine network security, IAM, encryption, and that's part of everything. It's a holistic package. So if we think about that API, it makes it fairly modular. If you think about it, a business creates an API like ChatGPT, and it's pretty easy for you to write an application that connects to it. Heck, you can go to AI, ask it to write the AI application of your choice, and ask it to connect to it, create an API, create the interface, and it'll do that for you. So, that's the key to think about with APIs is it makes it easy to connect to something. And because anytime we make it easy to connect to something, we have to secure that thing that becomes our door. Walk into a high security building. What do? Well, there's a guard there, and you have to prove that you are who you're supposed to be before you walk in. This is no different. It's the same thing along the way. We just use various things along the way. I talked a little bit about software testing. I'm going to discuss it a little more. So, if we say that organizations need to test their code, and I hope you would you just put something out there without knowing what the impact would be on your systems? I would. So you have to test. And how is that test being done along the way? Well, there's a few ways things can be done. One test that gets done along the way is considered a reasonableness test, which is basically is the application behaving in a reasonable, non-crazy manner. For example, if I go and I take my Apple Safari and I go to Google and I type www.gocloudcareers.com, I expect that to take me to gocloudcareers.com. That's my expectation. But if I put www.gocloudcareers.com in, and for some reason it says, which cat would you like to purchase? Well, I love cats. That would be not reasonable for our website. So, that's one of the checks, the things we check the software or somebody checks the software and it compares with a reasonable. Is it doing what it's supposed to? Now, other things is how it could be tested. They can do some comprehensive testing. Now, that's typically done on what happens when you do goofy things with your applications. So I go to a website. I showed you input validation, right? I enter something that would be an SQL injection attack on through that where it says fill in your email address, and it doesn't let me. That shows me that it blocks something big. If I enter something and ask to get something, query something, it comes from a database, and I ask how many people are in the world, and instead of giving me an answer like 7 billion or 8 billion, it says 600 billion people. Well, that's not anything close to correct. We've got a problem in that software or that AI system that we have. So those are the kind of things that we have to test along the way. Now, let's think about it. You can test in a synthetic environment. And how many of you are from networking and are familiar with an IXIA? I had a friend, Kush. Kush was a fantastic QA engineer. He was like the most capable guy with this tool called an IXIA. And what you would do is the IXIA, you would tell it what kind of traffic to generate at what rate. And he knew how to break a network bad component, whether with huge amounts of traffic. And he would test things and find bugs that you couldn't find. Now, what he did is he used a synthetic workload, but he generated huge traffic with that. Now, we write an infrastructure as code script. We spin up 50,000 virtual machines at 2:00 in the morning using some form of preemptible or spot instance. We now push real traffic and real use from patterns we've actually seen through those servers, and now we test it that way. That's some pretty comprehensive testing, and that's using like a live workload, real users, as opposed to the synthetic IXIA that's just generating traffic. So there's lots of ways that we can stress test stuff, and typically speaking, we need to do that from a security perspective. I want you to think about this from a perspective. I know I talked about editing. Can you see your own mistakes? No. Have you ever heard the expression, a lawyer that takes themselves as a client is a fool? Because they can't see their own mistakes. It's why we medical people are not supposed to treat ourselves. So instead of taking care and writing my own prescriptions, I ask my wife if I can't find my primary care provider because she's not me. Could you examine me, make a diagnosis, and give me whatever I need? Because she's not me, and she's a provider that can do that. Because I don't want to do it for me. Because I might not be actual objective with myself. So I want you to think about that. Now, let's talk about testing, and this will also talk about other kinds of testing as well. Now, I can do what's called white box testing. Here's what white box testing is. I give you everything about the application. Everything. You know everything about it, and you even see the source code. And then I ask you to test that software for vulnerabilities or problems. Or break into my systems or whatever. That's white box testing where you know everything. I want you to think about that. You basically give insider access to a tester. Let's assume that tester is trustworthy and honorable. How much more effective will they potentially be with that than if they had to figure out how to break into it on their own? Let me know your answer in the chat box. It's going to be much more effective. If you work every day at a company and you have a badge at that company, but you got fired tomorrow and nobody knows you were fired, is it going to be much easier for you to sneak in than if you've never been in that company in your entire life and it's a high security environment? You may notice on certain missions, for certain critical missions, people actually study ahead of time before they go in. That's the difference between a successful thief and someone that robs a 7-Eleven and goes to jail. The successful thieves, they look, they do some recon, they stake out the place, they figure out how many guards, how to get in, how to get not, weaknesses in the system, and they go and take what they want, and then they go flee to another country, and nobody even knows what they did. And then there's somebody that picks up a gun and walks into a 7-Eleven and says, "Give me the money on the register," and they're photographed along the way. Oh, that's the key to think about what you're actually doing along the way, because we're trying to test it from different ways and think about it. Now, if we do black box testing is how a true hacker would figure out how to hack you. The same way as the successful thieves would have to do. But since they wouldn't, given all the information, they'd have to do the recon. Exactly. Ocean's 11, great example, but anything like that. But if you think about it, if you're training a spy, they can't get caught. They're going to have real tradecraft and real knowledge. So think about that. Black box testing is you don't know how. You have to figure out how to break in. Now, that is going to give you a very good representation as a rule of what the average hacker could do. But it's not going to give you as many as the errors as you would get with that white box testing when the hacker's given everything about you and looking for every weakness you have. For example, you paid somebody to test your code for you. So that's black box testing. So if white box testing is I give you everything and tell you how to figure out what's wrong with me, and black box testing is I give you nothing and you have to use all your intelligence and capabilities and tools to figure out how to break into me, that brings us to gray box testing, which is a kind of a hybrid in between the two. I give you some information, but not all. And that way you have to figure out with the little information how you would break into the system. So that's kind of that hybrid approach along the way. And that is ways that things could be done, could be done. So I'm going to talk about a little bit of data security. And then I'm going to get back into databases as I touch a little bit about data security. So I know we just took a break, but before I do, does anybody have any questions on what we've discussed so far? Before I totally change topics.
Right. So let's see if we've got any questions. Great idea. I didn't have to prompt Mike this time. He did it on his own. So don't we hadn't gotten any questions yet, but let's give him a second to see if there's any questions related to the content, like you said, before we move on to the next I guess domain or topic or area, however we want to frame it. All right. Is it possible that analog reel-to-reel tape machines can make it back to data centers for enhanced security for mission critical workloads?
You know, what I love about that was security by obscurity, but security by obscurity is still not the best language. So right now, if I said looking on this call, and I could be totally wrong, I'm looking really quickly. But if I look on this call and I say, Ogol ima penindavil kronia, kronos, probably nobody on this call actually understood that I said I'm 52 years old. And the key with that is most people are not speaking Greek here. So that's security by obscurity. Now, all of a sudden, somebody that doesn't have a name that looks Greek because they married somebody that was Greek or something like that, and their name changed, understands what I have, and all of a sudden my encryption scheme is broken. So that's security by obscurity. Microsoft was a very big proponent of security by obscurity, and they used to talk about it with Windows NT 4.0. That's when they invented that NTFS file system on partition. And they called it security by obscurity because the only people they could figure out how to access those VIOMs were running Windows NT 4.0 versus Windows 95 versus Windows 98. Now, all you had to do to access it was steal somebody's hard drive, install Windows NT 4.0, and you were done. So that never seemed like a good security approach to me. So, you know, could we use something like that? Well, the key to also remember with reel-to-reel tape was it also was very slow. But what are we seeing more realistically, Pablo? We are seeing mainframes that are making a resurgence. And why is that? You can find mainframes with hundreds of cores and terabytes of DRAM that run very efficient code. And in many cases, they are very secure. They are very simple to run. They last all kinds of years, and they make, in some cases, better ways for banks to record transactions than cloud computing, which is why banks still are running mainframes and mainframe spending is going up. So if we start to look at what we're actually seeing and how would you secure, oh, if you look at a data center, I have complete control over it. And what I mean by that, I can control who gets on my systems, what kind of traffic is allowed on my systems. I can micro segment and do things that could never be done on a cloud provider. And I don't have to pay for any of it because it's all native to my network. And I can have much harder boundaries. But that's not saying that it makes sense. But what are we seeing? We are seeing a huge cloud repatriation movement where companies are going from the public cloud for security reasons back to the private cloud. So you may see more things like that. And I think, I know you'll see more things like that. So you may see people getting more hardware encryption, more hardware keys, and other things that enable them to be more secure. Because the problem is when you're in a cloud environment, you still have 100% of all the security weaknesses you have in the data center. But as soon as your cloud provider gets hacked, like when Microsoft Cosmos was hacked, you can be hacked too, just like their customers' information was stolen. When a system is going down to an outage, it's very easy to be hacked. So, you have to worry about them getting hacked and you getting hacked, as opposed to just you getting hacked. So you have to always think about that. So I don't think we're going to go back to tapes, but I think you're going to see for cost purposes and security people, a whole lot more people leaving the public cloud and going back to the data center. And it's
And,
cheaper in most cases.
if you want to know why I turned my camera off for a split second, that's because I took a moment to confirm there are companies, and you'd be surprised, I'm not going to say who, that never left the tapes and are still using the tapes.
Yep.
And I had to confirm, one of them I knew for, uh, uh, I thought it was going to be, but they got off 2 years ago. But there's still a couple of others that are still, that at least I know of, that are still using tape. So it I'm pretty sure they have their reasons, but
Yep.
I'll leave it at
Good
that.
reasons.
Uh, so another one. Do we have the same session management issues for on-prem developed applications as cloud native developed applications, i.e. passwords?
Yep. I've seen people do it in data centers. I've seen people do it in cloud. I mean, I don't look at the code ever because I'm an architect. But when it comes down to it and we have a problem and we're looking to figure out what happened, sure enough, I've seen it in the cloud and I've seen it in the data center. No, I've seen people make a lot more mistakes in the cloud. Because what happened, there was a short period of time, I'd say 1998, 1999, where no one knew what cloud computing was. So what they did is they hired people with a bunch of certifications that still didn't know what cloud computing actually was. So then you had a bunch of people on the cloud that were doing really terrifying things because they had no idea what cloud computing was, and all of a sudden they had a job. So there was a lot of that going on. So I've seen a lot more mistakes in the cloud than I have in the data center. Plus, the cloud providers are very hesitant to tell you how their stuff works. And it's very hard to secure when they don't tell you what it is or how it works. So a lot of people have not learned how to design the clouds or how clouds are built. So they're not able to secure them. So I've seen many more weaknesses on cloud just for that reason.
All right, so our next one is a very broad, vague question, but it says, please speak on a network of computers having modern, up-to-date operating systems as well as old operating systems.
So, at the end of the day, if you've got something that's harder to secure, like an old operating system, then you might need more firewalls or more something. But really think about it. You could be using BSD Unix. That is an incredibly secure operating system that's 50 years old. Actually, more than 50 years old, about 60 years old. And Linux all comes from BSD Unix. So I don't want you to think that old is less secure, but let's say you've got some old things, Windows 95, Windows 98, where there's no software maintenance on that, and they're still part of your system. What do you do with that? Well, what you typically do is you put them in a specific subnet or group of subnets. You limit what those subnets can get access to, and you mandate certain other things that are installed on those operating systems, things that you can put there like a host-based firewall or some malware protection or anything you can do to lock it down. So you minimize what they have, and then on those specific things, you add stuff. You make sure you've got quality of service on the network. So if somebody's computer got a worm because it wasn't protected against it, you couldn't protect against it, for example, that they couldn't send too much traffic on the network. So that's typically what you're typically doing in an environment like that is when you've got something weak, like an IoT device, then you've got to, which is hard to secure, then you've got to make sure that those IoT devices are very limited in what they can talk to and where they can actually talk to it because of those weaknesses. Same kind of thing in an environment like this. And then in many cases, if they're running the old Novell netware and IPX, and they're trying to tunnel that across an IP network, in which case, if they're using Windows 95 and 98, they might be. And that's where we start getting into GRE tunneling and things of pushing those things through an IP network. I've had to do it in the past. It presents its challenges, and it needs very good, capable people. So the people that can actually deal with this are some of the best that are out there. They're not going to be low-cost people.
All right, well, let's let you get back to the content, Mike.
Sounds great. So, talk a little bit about data and data security. Then I'll probably get in, if we have time, I'll talk a little bit about databases. So, if we think about data, and data is how do we protect that data? Well, first, there's going to be a lot of things we need to do, and I'm going to try to whiteboard a lot of this out to try to make as much sense as possible for you all. So go back to my trusty whiteboard because I really kind of like to come at it from this perspective. So the first thing that's part of determining data is who owns the data and what is the data. So I'll show you what I mean by that. So let's say we've got data. We've got a company's data. So under the company's data, we've got a couple of things that we need to think about with the data. The first thing is who owns the data. Maybe it's the CEO. Maybe it's your data. But if it's business data, does that business have the ability to tell you how they want that data secured? Yeah. Now, if it's pictures of your cat, that may not present itself as mission critical business data. I hope it's not, because I can't think of too many businesses that where the photos of the cat would be critical data. But we have to figure out who owns it. What else do we have to figure out with the data along the way? Tell me in the chat box. Because there's a couple other things we need to know. And if there were a CISSP, we'd come up with all kinds of funny names that you would have to talk about. So if I need to know, first is who owns the data. But what else do I need to know? Who's allowed to access the data, right? Now, would we ever be in an environment where we own the data and somebody else is handling the data? CEO may own the data for the business, right? Do we have a database administrator that might be working on that data? Do we have some data scientists that may be working on that data? Do we have some AI architects and AI engineers that are going to be designing a strategy around that data? So we have to determine who can have access to data and what kind of access that data actually needs to be. So hope that makes sense. Now, if you're in the EU and the GDPR has names, data custodian, data this, data that, data the other thing, depending upon the model you're in, you may have to conform or have certain data people. Now, let's talk about the kinds of data we might have. So let's say I have a couple of genius friends. They all have like PhDs and 107 IQs of 170. They may not remember to shower, but these are the geniuses that the upper 99.99999.9% smarter than the rest of the world. That could be in an environment that I have. Now, if I've got a small number of people that are creating that secret formula, that group is creating the secret formula for the next GPU that can outperform the NVIDIA H200 by 500%, this miraculous thing, at a half of the cost. How many people are going to line up to buy that? How much is that secret formula worth? Trillions. Because that could easily become the dominant AI player in a minute. So how important is that data? Pretty critical, huh? If it's worth $1 trillion, are you going to spend some money to protect that? So you have to classify the data. Now, that might be, top secret, restricted information, what have you. Do I have data on my website to some degree? That's public data. You expect the world to see it. Don't you think organizations have public data? Don't you think a drug company might need to publish data on a drug study to get it approved? Now, they may have sponsored the research to make it, and who knows what happens when somebody sponsors your research, but they have to provide the data to the public. So that's public data. Now, we might also have confidential data. What's confidential data in general? Data that we don't want other people knowing, but it's not so critical that it can cause us to go out of business. That could be confidential data. And then we might have internal data. So if any of you ever work as, say, principal architects at some point in your career, like a lot of the people I train, I'm sure will be principal security architects. And let's say you work for a vendor that makes firewalls. Here's what's going to happen. So let's say you're a principal security architect or a distinguished architect, and I have a lot of hopes for my students that they will be, especially my security architect students. So let's say that you're there. So let's say you're working at a security company. Now, here's ultimately what's going to happen. The security company is going to have a team of executives. And these executives are going to have a lot of information. Now, what might they know? They might know which products. They might know the pipeline of products. They may know the sales revenue before anybody else knows. If there's some kind of production problem along the way or a legal challenge that occurred along the way that most people don't know about it, they'll have access to all this information. And that's for a reason. They need to know. Now, who else is going to know about these products, and why do these executives need to know? So let's say there's a brand new firewall that's going to come out, a brand new security appliance. Why do some people need to know and others don't? This is vital security. Well, the executives are paying for it. So they need to know. So let's say you've got the sales executive needs to know when they can start selling it. Now, the marketing executive needs to build a marketing and demand generation pipeline for people to want to buy it once the product is there. Maybe there's some people that needs to speak to the media, so there's a team of publicists that need to know along the way. So the executives need to know this. Now, along the way, this is a security company. They've got this new security appliance. Now, all of a sudden, they need to sell it. So the first people that are going to know about it are going to be, say, the VPs of sales. That'll need to know it. They'll be they'll be your principal solutions architects, and I'll show you why. And then you're going to also have your principal engineers or your distinguished engineers, which are going to be the most talented engineers that you know in the company. All these people, for example, and I know I spelled principal the wrong principal, but we're doing it live in real time, so bear with me. So what's going to happen here is we can't train everybody with the new secrets of the future. So we're going to be training our principal architects on what that new product is and how that product will solve various business components and where the architectural strengths in the product are and where the architectural weaknesses of the product and where's this product sweet spot and where isn't it and what business problems it's going to be sold, designed to sell. Because the architects won't be able to design it without knowing this kind of information. And we can't tell everybody there because what happens when somebody gets quit or gets fired, they'll go tell the information to someone else. So we keep the information contained. Now, the principal engineers, they need to know this stuff too because they're going to be working back and forth to make sure the new features are integrated. They're going to be potentially dealing with the biggest and most scary clients that are going to be using these for early pilots. So the initial people that know are this. Then all of a sudden, along the line is starting to come out where now we start training the directors of sales as it's getting closer to release, and they still know, or maybe the senior directors. Now we're training at this point. We're training potentially the consulting engineers that the company has, the technical marketing engineers, for example. They actually typically new in this process, the marketing engineers, and then at some point. TME, the technical marketing engineers. So typically it's that, and all of a sudden it's ready to be sold. And now all of a sudden the principal architects, the principal engineers, the technical marketing engineers, they start coming in and providing training for everybody along the way that's going to be part of the sales. So sales reps, regional sales managers, sales engineers, basic solutions architects, and now they're going to get trained. And that's typically the way the information is contained. So the people at the top, the people that are going to be dealing with the future of that company, they're typically the ones that are at that top getting there. Your basic sales engineers won't get it until the end, once it's there initially. So that's typically what you're typically talking about along the way. Who owns it? Who has access to it? Who's using it? Now, that's the first component. Now, now that we know to think about it, how to classify it, well, what's the next thing that we need to worry about? Where's the data stored? Where does it live? How many people really think you're going to walk into an organization and they're going to have a digital filing cabinet and you're going to walk in that filing cabinet and have access to everything they have and it's going to be neat and it's going to be organized and you're going to know it all and it's going to be in a pure cabinet. It's going to be so simple. Well, I don't know how many of you Ever worked on a master's degree or a doctorate, say 30 years ago, before the internet was common, and you walked into a library and you had to find a book by some Dewey Decimal System, and then you'd get there and then the book wasn't where it was supposed to be because somebody either misplaced it or took it or borrowed it or what have you. Anybody remember those days? Well, that's kind of like data inside of a business. And if you're too young to remember those days, well, that's one of those things I don't miss, was trying to figure out how to find 15 sources of quality information from microfiche in the newspapers, microfilm days. So anyway, so we need to know where the data is. Where might our data be, realistically speaking? So I want you to think about the complexity of the data so you can figure out what problems we're actually trying to solve. So there's going to be a lot of places. So it's going to look more like this. So let's say we've got our data in. Most organizations have relational databases, right? That usually store transactions. So we can call these relational databases. This is like MySQL, Oracle DB, MariaDB. Well, Postgres is a relational database, but it could be used for other things. Microsoft SQL. So most organizations have some data in a relational database. Now, what do they typically have in a relational database is structured information. Like, you bought this product at a certain price. Now, most organizations in today's world work with semi-structured or information as well. And they use what's called a NoSQL database. And if you're ever taking an AWS or an Azure certification, I don't want you to think these are like brand new modern things. Relational databases are 60 plus years old. So are NoSQL databases. So NoSQL databases are great for unstructured information. So when my wife is outside the house doing gymnastics and I want to watch the new F1 movie, which I bought and haven't had a chance to watch yet, I could turn on the speakers, I can turn on that sound system, and I can watch that movie. And if I stop midway through that movie because I bought it from Amazon, I'll be able to start it in the same place. That is not exactly structured information where I'm at in this F1 movie that I have to see, or the new John Wick ballerina movie, which I highly encourage you to see. It was quite good. But anyway, that's just me. I liked it. But, they're going to have information there. Now, a lot of businesses have data warehouses like Postgres, and they put all kinds of information in this. And what's the point of these data warehouses? If you don't know what it is, you can't protect it. So this is long-term, lots of huge scale data that they stick in a data warehouse. Why are they doing it? Well, if I can go back and look at information over history, I can make predictions from the future. If any of you have ever studied history, you can see we keep making the same mistakes again and again and again. It failed, so let's try it again 30 years later. It failed, let's try it again 30 years later. It'll fail again. You can predict it. And that's what businesses know. Businesses start collecting data in data warehouses so they can start making predictions. This thing didn't work the last 20 times. Let's not try it again. This thing worked. We sold more. Let's do it. Let's go back. So the organizations start having these data warehouses. Now, this is a lot of your information that's going to be semi-structured or structured is going to be here. But organizations, whether they're the data center or the cloud, they're going to have these storage. They typically have object storage environments. And what's going to be in here? Anything they want to store there. So now you've got object storage. If they're in the cloud, it's like Azure Blob, AWS S3, whatever you want to call it in the data center. So there's going to be object storage that's going to have some information. Now, we may also have some file servers along the way. Maybe 10 servers need to access the same thing. So we'll have file servers, which will also have storage on it. And guess what? We might have virtual hard drives for our virtual machines that are sitting in the data center or cloud. And that could potentially be on the servers themselves, or it can be in block storage, which is attached to the network. Starting to see this is good, could be an issue. And where else could it be? Well, everybody has a hard drive themselves, right? So all your PCs could also have storage on them, which could have vital information. But let's not put that in here. So the key to remember is you're going to have storage in a lot of these places. So we're going to have to make sure all of this is secure. So first we have to find it. And then we have to put controls on it to make sure that we can't be hurt with it. So, does that make sense so far? Okay, now I just want you to think about something else, and I know we're going to do something with encryption the next day, but we have another day where we discuss encryption. So I want you to think about this. If somehow you get access to the data or one of these servers, or you're in the cloud, you're in AWS, you're on the same storage system as 1,000 other customers, one of those other customers commits fraud, and somebody like the FBI goes in and they take all the servers from the cloud provider. And of course, your data is backed up somewhere else, so you can get it up and running in a certain period of time. But your data is now seen, but is now out there. Is that a concern? Let's say somebody at the FBI now has access to your data. Now, a couple of things can occur along the way. Maybe there's proprietary data, and somebody can see it at the FBI, and they'll do insider trading. Not saying they would, but they could. Now, somebody at the FBI or whatever organization is looking to your data may have just found the secret formula for your new GPU, which could bankrupt your business if everyone got it. None of this is a good situation, right? A group of a group of mercenaries breaks into a cloud provider's data center and steals 5,000 hard drives along the way and 10,000 servers to see what they can do with that information. So we have to make sure that information can't be used. So I want you to think about three kinds of encryption that we're going to talk about with this data. So there's really three. The first thing that we need to know is that if somebody breaks in and steals the hard drives, that they can't get access to your information or any of this along the way. So what are we going to do with that? We're going to encrypt this storage. So if you're new to encryption, and I used Greek because it was weak encryption, if I speak Greek and you speak Greek, we can talk to each other. So not the most effective form of encryption, but it's an encryption. Now, if I come up with some form of an encryption, and when I encrypt it, I encrypt my data with some type of encryption that takes my data and makes it something that is near impossible for you to figure out unless you have the decryption key. Can you access my data now without the decryption key? Oh. So is encryption become 100% mandatory of everything, especially in a cloud computing environment, when somebody can just take your stuff at any one time? And they're not even your systems. So encryption becomes mandatory while it's at rest and while it's stored. That means every drive, every server, every block storage environment, every object storage, everything gets encrypted. Now, here's the second side of where we may want to protect our data. Most people are familiar with the first two, but we have to talk about the third because the third is also critical and most people are unaware of it. The second kind of encryption is in motion. And I know I did this a little bit when we talked about the data. So what does that mean? If we go back to the same diagram we have, we need to make sure that the data hasn't changed. So here we have a medical application. We have a physician over here. We have a nurse at the hospital. We have a hospital, and in the hospital we have a nurse. Now the nurse has a patient that's not doing well. So here was the process. At 2 o'clock in the morning, the nurse's patient has a fever. The nurse thinks has pneumonia, and the nurse is very concerned about that patient. So he calls the physician and says, the patient has this. I recommend giving the patient this. And the physician says, yes, give this patient this medication at this dose IV now. So that was the process, the way it used to work. So the nurse would say, my patient's blood pressure is bottoming out. And we'd say, fine, start a neosynephrine drip and titrate to a blood pressure of whatever. Now that was human. How did that work? Well, the nurse knew what the doctor sounded like. The doctor knew the nurse's voice. They knew what the information was. They exchanged information and the communication occurred. Now, all of a sudden, this is electronic. Now, all of a sudden, I want you to think of the implications of this. The nurse calls the doctor via an electronic message that says, patient has low blood pressure, and I need to give what's called the depressor, like neosynephrine, for example. And the doctor sent a message back, and then a hacker changed that neosynephrine to a drug that's designed to lower blood pressure aggressively, like labetalol. Okay, so let's think about this. The nurse says, I need something to raise blood pressure, and the system is hacked, and the system tells the nurse to give a drug to lower blood pressure. Do we see we have a problem here? Like a big problem? Well, I'll make it a more obvious problem. Patient has chest pain. Nurse calls the physician and says, patient has chest pain. I would like to give 2 milligrams of IV morphine. The physician writes an order for 2 milligrams and someone changes it to 2,000 milligrams. Patient stopped breathing and died. So, what are we really talking about there? We're talking about the need to encrypt that data in motion and the need to make sure that data hasn't changed. Does everybody see how critical the integrity of the information is? If so, please tell me in the chat box with a yes or I get it. But integrity of that information can be life or death. If the money in your bank account isn't what it was supposed to be, that's not a good situation. So encryption gives us that the message can't change. So at the same time, let's go back to our encryption example. We're getting something else. Not only do we have a guarantee through encryption that the physician and the nurse are who they claim to be, we also are guaranteed that the messages haven't been changed. That's occurring through a hash. We'll explain that when we do the encryption day. So we also don't know that the patient that was having chest pain was named Leo the Lion. We don't know that it was Leo the Lion. So we've got that kind of confidentiality that we're getting away. And that's why when people are going back to them, I'm trying to tie the pieces together because there was such great questions. So that's what we need to do. So that's encrypting the data in motion. Here's where most people get it wrong. And I see it all the time. So let's think about this. If the data is encrypted when it's stored, so let's say this is your server, and the data is encrypted when it's stored. So the hard drive is stored. And this doesn't matter if it's a physical hard drive sitting here or a block storage in, say, a virtual machine. Doesn't matter. Same concept. So it's encrypted here, and it's also encrypted when the data is flowing to the other system. I showed you that. So this is encryption at rest because it's rest. Then there's encryption in motion. This is also encryption in motion. You may also hear it called flight, but motion, whatever, same concept. So it's encryption in motion. Now, I want you to understand this. Let's go into this system and let's look at the architecture of the system. Whoops. So on this system, we've got a CPU, probably 2 if it's a server. We've got some DRAM on this system, for example. These are our little DRAM strips, for example. I'm not going to draw a lot of them, but, a modern server can have 6 terabytes of RAM, 8 terabytes of DRAM, fair amount of RAM, especially in high performance compute. And those servers are much cheaper in the data center, potentially by 10 times than in the cloud. So we've got our RAM, and here's typically what happens. When we need the data, it comes out of storage, it gets decrypted, then it gets sent to DRAM unencrypted, processed on the server unencrypted, and then it's stored encrypted, and then it's stored when it was sent to the next system. Does anybody see a problem with that? Yeah, our data is not encrypted when it's going to the processor. Now, let's think about the implications of that because I want you to see what happens. Now, if I'm in my private data center and it is my server and I own the server, how serious is it for the as a rule if something is unencrypted between the hard drive in the and the server in my own system in a building that I own that I've got tight controls over? It's not optimal, but it's no big deal. So why am I talking about this? Well, a lot of people have things in the cloud, right? Now, here's what I need you to understand. This server in a public cloud might have 100 different customers on this server. So now me, potentially my competitors, potentially even media providers, potentially in the press that could spill secrets like crazy, all have access to this theoretically once it goes from encrypted storage to DRAM. So what's the workaround of this? Well, in your data center, it's not such a big deal, but it's called homomorphic encryption. And what that enables you to basically do with homomorphic encryption is somehow process it while it's still encrypted. So it's encrypted in storage, it's encrypted in DRAM and the CPU, and then you encrypt it when it's sent. Does everybody see how that would protect data? Because I'm really trying to put the pieces together of protecting these things. So, okay, Iwadi, that's totally fine. So let's look at this. So let me try to talk about it at three times or an extra time because I really want to make you think about it. So encryption in motion. Let's look at the thing. So now we take our data. The data comes out of the encrypted storage and it's now usable. The encrypted data is sent encrypted to the DRAM and the CPU. It's processed when it's encrypted and then it's stored and sent when it's encrypted. That's using homomorphic encryption. Now, the old way of doing it without it is you're going to have to take the information out of encryption. You're going to have to unencrypt it, send it to the DRAM, and send it to the CPU unencrypted. While you're all sitting on a cloud provider that has 50 other customers right there. So you got it. Wonderful. I'm glad we actually addressed that. So I wanted to make sure that made sense. Because to me, that's a very critical component that we want to deal with in designing a system like that. So now let's determine other things as well. Let's talk about some data access controls and what I mean by that. Oops. Are any of you managers or have been managers, for example, where you have employees and you've got an HR system where your employees uh, pay is and approvals up or down to promote them and do any of these other things? So let's work on two assumptions. We've got an HR system. You've got a great job as a security architect in a company. And that's what I want for all of you. Some of you are actually training to do that, but that's what I want for all of you. So in this particular environment, you've got two systems. And this is a principle that's pretty important from security. So you've got the employee, and the employee sees some things. Now the employee, when they access this database that has their payroll, the employee sees what the employee needs to know to how to adjust their pay. So this is employee related. Now instead we have the manager. Now we've got the manager over here. Now the manager system does not just get employee related thing. The manager system gets employee data, the ability to provide raises, the ability to approve expenses. And they get it when they slog into the same application, the exact same application as when the user logs in with different permissions. So you may have seen this. Certain engineers will have access to what others do and more. That's just the principle of giving people what they need to know. So I want you to bring that back and think about the implications of it. If you're accessing a database or you're designing a system for database security, everyone does not need to access the same thing, right? So maybe the manager has the view of some things. Maybe you don't get access to it while you're using the same database. And that's typically called views, where you can create one view for one level of access and another view for another level of access. So that's typically what we're talking about with that. And this could be at every object dealing with object stores that we're dealing with. Now, if we have this environment where some people need to access the information and are getting it, and some people don't need that access to information, so they don't get it. What happens if out of nowhere I have a consultant that needs emergency access to the system? Or one of my employees that needs access to another level? Do I just give them this kind of access a year in advance in case they might ever need it to everything? Or maybe I come up with some kind of just-in-time access program where all of a sudden something needs something. I give somebody a temporary access for a week to do their job or whatever it is, and then I close that access when we're done. So I want you to think about that. Early in my youth, when I really didn't understand what was happening at the time, I worked as first a paramedic and then apparently the paramedic and then the head of IT for this uh, ambulance service in Pennsylvania. Now, when I worked in the ambulance service, they had a database which had a whole bunch of problems. And one day I said, I'll fix it for you. And I did. Somehow I just knew what to do. It was something I was just naturally good at. And in the process of fixing the database, which wasn't working, I started buying some database books to figure out how I could tune it and help it for my boss. He was really good to me along the way. And as soon as I was in the process of that, my boss, the chief's brother, said, I don't think you should let Mike start looking around. And at that point, I was like, I better walk out of this office. And what I heard was, Mike's a smart guy. He might figure some stuff out. And then my manager answered it. Mike's like a son to me. And I've treated Mike like a son, and Mike would never hurt me. So that's not something I'm concerned about. Do you know what ultimately happened as I looked through that database in terms of how to perform? I found out that the person's brother had been embezzling by employing his children and his spouse, and they were all getting paychecks through the system. Now, what did I discover and why did I talk about this? When only one person has access to everything, they can do some pretty terrifying things. So when we're dealing with security, potentially securing critical things or clear data, we want to do what's called separation of duties. We don't want anyone to be able to do just about everything. We initiate some kind of mandatory vacations, for example. We initiate environments where somebody has to fill in periodically. If two people were looking at that system every day, do you think that person could have embezzled and had 16 different people's paychecks coming out of it? Or do you think somebody would have caught it real fast? So we always have to talk about separation of duties. It's the same reason why someone on a submarine can't launch a really big, scary weapon without getting authorization and code numbers and get several people along the way. It's designed as a protection method. So that's why I really want to go in there and talk about that. What happens, and this is going to be critical, separation of duties, mandatory vacations. You must go away for a month. I must have someone use the same systems as you with your access level for a month. It provides that inherent management to check it. So we talked a little bit about keys. Now, how many of you forget your passwords? It's not easy anymore, especially when everything needs to be this gigantic thing. Or you're a little security obsessed like me and you have 60-letter passwords or something cuckoo like that. So when you can't use something stronger. So if we actually think about that, here's what I need you to think about. It's now encrypted. There's encryption keys, right? What happens if somebody steals your encryption key? Leo, I just taught you Greek. Now, how effective is me speaking in Greek right now? Now that somebody else speaks Greek here. Leo has the encryption key. It's all done. So we always have to think about encryption keys. Now, the cloud providers will manage our keys for us if we want it. How many high security environments let the cloud providers manage their keys? Here, I'm going to allow somebody else manage my keys for the most critical encryption thing in my business. And when that cloud provider gets hacked, now they got my encryption keys too. So we will always have to think, if we're dealing with encryption keys, we have to manage them. Can we use the same key all the time? So we have to rotate those encryption keys. And how often do we rotate those keys? So we're typically going to need some type of serious key management system, because most likely if it's super high security, the company is going to have to manage it on their own. Now, when it comes to key management systems, there's software systems and there's hardware systems. If it really matters, you're using hardware keys, or hardware. So I want you to think about that. Now, if we think about data, we have to think about, how do we keep it private? So I went to a doctor's office at a local hospital, and here's what happened at the check-in point. They had 50-inch TV screens that you were supposed to put your driver's license in, type your name, your birthday, your email address, and your phone number on that screen while everybody could see you in the entire room. Now, I looked at this and I walked in and said, can I take a picture of this and post it on LinkedIn? Because this is the worst HIPAA violation I've ever seen. And then I remember that I consulted to that organization and I felt bad about it, so I didn't do it. Because I didn't want to encourage hackers and give them things easier to deal with as well. Here's an extra tool. Here's a great place where you can steal patient information. But the key is, that was just ridiculous. It made it easy for people to see. So what a great thing in the chat box. The glare screen protectors, that was a great idea. And that would have helped us a lot of way. But what are we really talking about? So one of the things is masking your data along the way. So have you ever seen this? And these are some data privacy techniques that we're going to talk about. We'll draw it out. And I'm going to ask you if you've ever seen this. So you log into a website and all of a sudden you go to the payments thing, and here's what you see. You see XXXX, 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 and then the last four digits of your card, 1, 2, 3, 4, for example. Have you seen that? Now, if you're on an airplane and you're logging in to check your bank, which I would not do, at least the person next to you can only see the 1, 2, 3, 4. So that's one way that we can keep data private. We can just not show it. We can mask it along the way. And that's going to be pretty important. If we don't display the data, you can't get access to data. So that's one of those things that I always want you to think about, is doing things like this. Now, we can also tokenize the data. We can swap, but tokenization is basically swapping data for a token. So we can tokenize it. So the data is Cindy's birthday. So that's the data, not that it's high security data of my cat's birthday, but whatever. And instead of seeing instead of seeing it, we replace Cindy's birthday with a token. And if you have the token, you can get access to Cindy's birthday, but what's going in as a token that's swapping the data.
Mike, are you sharing your screen?
I probably did not. So thank you. So let me kind of do that again. So let's say we had Cindy's credit card information. And you know who pays the cat's credit card bills. Or I should say my wife does the shopping for it, but whatever. So we've got Cindy's credit card information. And I know I used an example of a different example, but let's say Cindy's credit card numbers are, for argument's sake, we could replace, let's say that's her credit card number. Was trying to do a count on the way up, and somewhere along the line, it got a little goofy. But anyway, so that's what we have. We can swap this out for a token, and we've got a token system that when you actually provide the token, will actually give you the information later. So we don't have to keep the data in the database. We can keep it somewhere else to keep it secure. That's tokenization. And there's lots of ways that we can de-identify or anonymize the information. So if the information we have here is Cindy, and then Cindy's address, and then Cindy's birth date, for example, and then we have Cindy's medical records or Cindy's health condition medical records. I can change this to some other value. We can call this user one instead of Cindy, and then I can replace user one with user with no address. I can get rid of the birth date, and then I can still keep the medical records there that are not Cindy. So we have no idea who it is, but we can now examine the data of a population of cats without knowing the cat's names, anything about the cats, but we could take thousands of users like this. This could be done for people in a drug study, a disease study, but that's where we basically anonymize it. We de-identify it. So you can't figure out what it is. But it's real data you're getting. So if we were going to look at a bank's trades, for example, and we were going to evaluate the profitability of those trades or whether the trades make sense, we could take all the people that make the trades off, all the clients' trades off, and then we could track those transactions with de-identified information. So that's that kind of concept of anonymization. So there's lots of things that we could get into if we were going to go dive deep in a data security architecture program, but that would go beyond, what we have allocated today. But so far, that's what I want you to understand with those types of data privacy techniques that are going to be part of it. But we're not done. So I want you to think about this. And this is why it all goes back every time someone asks, what does it take? It takes everything. So if you're here, if the data is here, and the hacker is here that wants the data, but there's a firewall in the way, it's going to be pretty hard for that hacker to get to data because we segmented off with the firewall. Now, if we're in the cloud and they're in the same VPC, oops, sorry, I didn't mean to do this. So I want you to think about, we're always thinking about how do we micro segment. So I didn't mean to do this. So if we're all in the same, in a cloud provider, say the same VPC, VNet, whatever have you, all these things are basically in the same environment. So if we don't put this firewall in, a user can go, it's a little easier. If we've got a firewall, we're a lot protected. It's hard for the hacker to go through the firewall to the data. Now, if we further segment this system, that this is one VPC, and let's say the hacker got on, so this is a VPC for the data, and then this is another VPC for the website. Even if the hacker got access to the website, The website's in a different VPC or VNet, then so it's in a different one. So there's no connectivity unless we enable VPC peering between the website and the data. So even without a firewall, it's segmented that the hacker couldn't get onto one VPC or VNet and jump to the other because there's no routing enabled between them unless you did. So the point is that we want to use it all. It's never a one thing, so we're sticking in the network there. Now, if it's a private subnet, it's hard to reach from the public. So we're looking at every single thing along the way. Now we've got a database. Let's say this is a database. Let's go back to it. And that's why I just want you to think about all the stuff that's going to deal with our databases, our data. So let's pretend this is our database. Do we think every database is perfectly designed properly? No bugs? No weaknesses? Okay, so, or for example, this is Microsoft SQL Server and it's running on Windows Server, whatever. There ever going to be any bugs on Microsoft SQL Server? Everybody has bugs. There potentially ever going to be any bugs on Windows Server? How many updates does Microsoft push to your computers every day? Now, I don't want, but too many. Now, I want to make it clear to you, I'm not saying Microsoft's OS is a bad operating system. I want you to think trade-offs. Does Microsoft's operating system work on every computer in the entire world? Does it work on 20-year-old hardware, 30-year-old hardware? The TSA is using computers from 2000. Not the TSA, our air traffic control. Windows still works. So Windows enables everything to work, which is why businesses use it. Now, if you enable everything to talk to you, everything, you're more at risk, right? So if Windows has more vulnerabilities, it's not because it's weaker. It's because it does so many things. And the fact that it still works to me is absolutely incredible. Like, how do they make this thing glued together? It's got every exposure possible, but it's got every capability possible. So it's all what they're trying to develop and what they're trying to get it to. So that database itself, right, is probably not secure by design, or it is, but it's not perfect. So on this database, we have to do things. So what about the operating system of the database? Has to run on an operating system, right? Do we think the operating system comes, when it comes from the factory, do we think it comes secure or do we think it comes insecure? And why? It comes very insecure. I'll tell you why. Can any of you tell me why in the chat box? Well, how many of you, and here's the reason why, how many of you would be able to go to, say, Arch Linux? You want to install an application, and first you decide, you find the code for the application. Then you have to compile the code potentially because there's nothing been there. Now that application has a dependency of 10 different other things on your Linux machine. So you've got to go find all those things, install them all from the command line, and then compile your application. What percentage of people could do that? Very small percentage. So your Mac is designed to make things installed easy. Your Ubuntu system with that little software store where you just click it and it's real beautiful and it snaps right in. Or any of these other things, they're being designed for convenience. So once you design for convenience, you effectively design for insecurity. So what does that mean? It means on a server, do you need to play video games on it? No. It means, do you need Skype on it? Probably not. Do you need Microsoft Word and PowerPoint on it? Probably not. Do you need half of those features that come with the operating system? No, so you remove it. And you do this for Windows and you do it for Linux, because if you are open and communicating on a certain manner, then you're not there. You create a 2-inch slit outside your windows to look at, and it's a steel window surrounding you. The only danger to you is through that 2-inch slit. Now you fill that 2-inch slit with 8 inches of Lexan, you're pretty secure behind that 2-inch slit and your 12 inches of steel that you're sitting behind. You really are. So the key is what we're doing is we're locking down everything. Now with the cloud, since I know somebody put it, you have to do two things. One is you have to hope that they patch their hypervisors and they patch their control plane and all that's perfect. And then you still have to manage your server and your operating system on it. So it's the two risks versus the one risk to think about. But it's the same thing. So that's what I want you to think about those servers. We have to harden these things. So what does that mean? We put a host-based firewall on this thing. So maybe on the device itself, we put a host-based firewall. Maybe we put some anti-malware things that are sitting on this server. Maybe we put some other things along the way, some host-based IDS, IP systems, we pull stuff off. So every system we have has to be hardened because it all comes weak. So the operating systems might need to be patched. The databases might need to be patched if there's a vulnerability there. So I want you to keep that there. Now, here's something that I want you to think of from a data privacy perspective and a data security perspective. And then I'll talk about how this can be done. So if you can walk into a store, let's say you walked into a store and all of a sudden there was a nice suit. You popped the suit in and you could walk out of the store with the suit on and nobody stopped you along the way. That probably wouldn't be too good for the store, right? Because people would just pop it on suits and walking straight out. Go in a t-shirt, leave in a nice suit. So if we think about that, the same thing applies to data. Can people get the data outside of our systems? Can they steal it? Okay, so we've designed the secret formula for a new drug that kills COVID instantly. And it actually works. How many people are going to buy that drug and take that drug? A whole lot. So the key is we have to think about what these things are actually worth and what we're trying to do. So how do we keep people from stealing that drug formula? Well, I can have some very scary physical security people checking on you on the way in and the way out of the door. But what if you've got a shoe and the shoe's got a little compartment and you popped it in there and we can't find it along the way and you can steal it by putting it on USB drive? Maybe. Or what if you could set up a back channel on the network and let it go? Or even worse, what if you can email me the secret formula of the new thing? Should I allow that as a business? Absolutely no. So if I know what's critical because I classified it, right? I need to know what information you can take and what information you can take. You take customer marketing information home. Do I care? The publicly facing documents? I don't care. But if you're dealing with real information, I do care. Okay, so now you're dealing with a weapons manufacturer. Do you think they're going to let you stick a USB key in and walk out with a USB key on any of their servers? What are they going to do? They're going to break those ports. You can't plug into them in the first place. Or they're out, or they're also going to put some software, some data loss prevention software on the servers. So I can't let you do that. If you're looking at really critical information that's so critical, can I let you be attached to the internet when that occurs? So I might have you in a room which has no internet and no radio waves, blocked by Faraday cages and other things. So we would think about that. I can't do that. So how do we keep you from doing it? Well, there's a couple of things we can do. And I'm going to talk about what those type of tools are, because we have to make sure the data doesn't get lost along the way. So we've got a couple options here. So one is, this is the server. Let's say it's a physical server. And I'm going to show you how scientific we can get and how we can start. One is I can just put software on here that when you try to use a USB key and you plug in the USB key into this USB port over here, so you try to plug this in here, I can just make it that you're not allowed to copy anything. Every time you do it, the system denies it. I could. And some companies do that. What do we think we're doing in high security companies? We're making sure we might unplug these potentially from the motherboard cables, if that's possible. We might stick in a screwdriver. So now you've got software in the thing. You try to break it in and you're not allowed. And if you try to stick it in the port doesn't work. Did I get more secure this way? Now, what if I did this? What if here's the internet connection? You know what? So here's my internet. Here's my firewall. So we're safe from the internet. Ah, this will make it better. Ah, that's better. So we've got the internet. Now we have let's say a couple of firewalls or a next generation firewall. So we've got some good firewall stuff going on here. And not only we have that, we've got a good firewall. Now I've got a data loss prevention tool that sits on my network. So first, I've got software in here. So if you try to jump into a USB port, it doesn't work. Then I broke the USB port. Now I stick this data loss prevention tool on the egress port of our network on the network. Now this thing sits there and looks for patterns of data. That critical data, you're not allowed out. 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 So these network-based data loss prevention tools are applied to the egress or the exit of your environment, and they will make sure that data is not sent out based upon a classification strategy that you've created. That's called data loss prevention, and we can apply it there. So far, does this make sense? Now let's talk where data might be, which could also be terrifying. Now you decided that you're going to use Microsoft 365, for example. Great product. And it's a cloud-based install, so you're using it over the internet. Now, at the same time, some of your users use the Google Office toolset. Now you're also in AWS. For a SaaS application. Let's just say this. Do you have any control over Microsoft 365 and its security? You have control over your usernames and passwords. That's pretty much it. In a cloud-based thing, on a SaaS-based environment, you have no control over what data leaves their system. What happens when the Microsoft is hacked and you now connect to them? Is that a bit scary to you? Can you control AWS's software as a service and make sure that it works as designed and they don't have any bugs? Or how about the Google Office while we're at it? So when we deal with software as a service providers, I want you to understand this. The more we connect to, the more likely are we to get hacked through them. Everyone we connect to is an opportunity. Everyone we connect to is a threat. So we have two people in a room. They are secure. They are both healthy. We've got no problem, right? We invite two more people and they're all healthy and we've got no problem. We now hold the wedding for 275 of my best friends. Poop, somebody gets COVID or somebody gets the flu. Why? Because we took a lot of people and we had a whole lot of exposures. How many providers have gotten hacked this year? Well, Microsoft admitted it. Other providers were just down for suspicious reasons. Why? So the key to think about is we have no control over anybody else. And if you ever deal with software as a service, you got nothing other than IAM to secure them. So what might we do? So, and there's a couple of ways this can work, and I've got some YouTube videos on this that I encourage you looking at cloud access security brokers, as we can do something like this. We've got a user over here.
Mike, can you share your screen?
Thank you. So we've got a user. And the user, which I spelled in a really horrible way. So the user wants to access Microsoft 365. So normally what would happen is the user would go to access Microsoft 365. They would go over here. Microsoft 365 would ask them for a username and password. The session would be set up. And now that user can access it, but we have no control over anything. Now, what we can do instead is we can use some form of a redirect, like a DNS redirect, and all of a sudden, the user decides that the user wants to access Microsoft 365. So the user plans on going here, but gets redirected to this cloud access security broker. The cloud access security broker authenticates the user, determines who they are, what they're allowed to actually do, and can enforce certain security policies. And then the user connects either through this or directly to Microsoft 365. But there's usually a tunnel where they're monitoring things. So assume you go this way and assume that it looks like this, where it's done in a proxy environment. You're connected to the cloud access security broker. The cloud access security broker, that's a really ugly looking wide area network connection. Let me see if I can make that look a little prettier. Okay. So now we've got the cloud provider that's got another tunnel to, say, Microsoft 365 if it was done in this manner. So now look at what happens. Now we can have this cloud access security broker make sure that your data is encrypted along the way, because it's all going through here. Now you decide that you want to take the secret formula off of Microsoft Office 365. You hit the cloud access security broker, and the cloud access security broker says, you can't do this. You don't have the permissions to this, and it just destroys it and drops it, and it never gets to the user. So we may be using cloud access security brokers for this reason in software as a service environments, because in software as a service environments, we have absolutely zero control over any of what they do. So it gives us the ability to police what the users are able to do and try to control what they are doing on a system that's not ours. Now, when it comes to protecting our data, it's pretty important to know who accessed it and when. Data is missing. I see who the last three people are that accessed the data, and I can see who stole it, or who deleted it, or who just accidentally made a mistake but deleted the data and overwrote it. Wouldn't that be important to know? What happens if a hacker keeps trying to hack into the database but keeps getting blocked by the firewalls? Should I know about that? I got a user that entered the incorrect password for 15 times, and for some reason we didn't log them out. Should I know about each time they tried to log in? So the key here is we've got to do a couple of things. We've got to start collecting this, and we'll talk much more about that when we discuss security operations on another day, but we have to collect the information, right? So everything we have, I want you to think about it. I want you to think about the number of firewalls we have, the number of access control lists we have, the number of access requests we get on any one of these systems. Pretend you're JP Morgan Chase for 30 seconds. By the way, prior to the AI boom, they had 2,000 AI professionals working for them. Prior to when most people thought about AI. To put that in kind of context, that's how big these systems are at a global bank. Now, they may have 1,000 firewalls. They may have 10,000 routers, a dozen data centers in multiple countries, a couple of cloud providers. We need to monitor that. We need to figure out what's going on and where. And I promise you're not going to do it on AWS CloudWatch. We're going to need some kind of tool that's going to take all of this stuff from all of these environments and be able to aggregate it for us to look for. To see that Billy Bob tried to hack into this system 27 times. And Billy Bob's brother, Tony Bob, making up a name as we go along, Bob got this far, and accessed things. And Samantha Bob did this in a coordinated attack all at the same time. I have no ill will towards Bob. It just seems to be a name I keep picking up for fun. But, that's really the key that what I want you to think about. So all these systems somewhere along the line with our data. And again, this is going to go back to everything we do, which is why I spent a little more time with it. We've got to log these systems. And then I'm going to talk about the last component for the last two components of data security. So if I've got this, bear with me. If my firewalls are sending me logs, and here's where I want you to see the difference. If my firewalls are sending me logs, I'm getting logs on my ACLs, my applications for which we have 50 different applications. They all have their own logs. Now we've got the login, the IAM systems that have their own logs. For those of you that are familiar with networking, you probably realize how many syslogs the routers and switches do. So let's call this syslog. The Linux, we've got our Linux servers. They're going to be sending 1,000,001 of these logs, usually syslog, but we servers have their logs. There could be 1,000,000 log entries every second in a giant enterprise environment. Now, how many of you are going to look through 1,000,000 log entries a second and be able to make heads or tails of it? Does that seem something simple for you to do, to just kind of look at these logs and go figure stuff out? I can't do it. My wife, maybe, because she can see wacky patterns. It's pretty terrifying, but not me. It's just too much data. So, how do we deal with this? So, if we look at this, and let me kind of show you the old world versus the new world, and this is where the new world gets both more secure and less secure with AI at the same time, because we use it, but the attackers use it as well. So if we send all these logs to a SIEM system, and here's what the SIEM system is used to do.
Mike, can you share your screen?
Yes. So we would send all these logs to the SIEM systems. And all these logs would be coming from else. And honestly, this was the coolest thing you could think about when these first came out. So now all your logs are going here. Now all of a sudden something happens. And what are you doing? Somebody would be smart enough to write a good script, and they'd see that these servers had an outage at the same time that we had a bunch of privilege escalations at IAM. At the same time, somebody breached the firewall and the firewall sent a log, and it all made it to this system. And that would help you figure out what happened when you had millions of logs. So this is cool, right? But what changed? I mean, AI is not new. I've worked on it for 20 years. David Lithicum, our chief AI instructor, has worked with it for 35 years. But what's really changed? The computational power is there, and AI is in everything. So what we ultimately have now is we have these source systems, which are kind of the same, which kind of are part of this environment. And what the source systems will do is they will basically use AI, and the data will be sent to these source systems. And the source systems can look and say, hey, wait a second. We got a problem over here, so let's do something about it. And that's putting AI in defense of our data. So the next thing I want to talk about is data lifecycle management. Okay, so you go to a hospital for a family member goes to the hospital. And, for about 30 days after you leave the hospital, maybe 3 months, you may have to see a half a dozen doctors that you went to the hospital, and you may need to get access to those records. So that hospital keeps those records for, say, 6 months readily available. Now, then they keep it how long they're required to keep it legally available. It could be 3 years, it could be 7 years. It's usually 3, but depends on where you're at and what the rules are. At the end of 3 years, if you don't go back to that, if you're not planning on going back to that hospital, is there any benefit for the hospital knowing about your broken arm 3 years later and keeping records of that in their systems? No, not at all. Now, if they keep a record of you and your broken arm in the system, and somebody hacks in the system, even though your data of you and your broken arm is meaningless to them, it's not meaningless to you. And when someone hacks that system and they get that data about you and your hospital stay, that's not a good thing. Now, first, that broke in the US HIPAA, which means now you're getting fined. And it didn't help the hospital even 1% to hold that data. So that brings us into the world of data. Understanding everything that we have can be used for you and against you. If a criminal commits a crime and it is on video 24 hours a day, those police are going to lock that person up. Likewise, if the person's not committing a crime and there's video of them all day, hopefully it won't be used against them, and hopefully that will disprove that they've committed a crime. But the key to remember is old things are still valuable to attackers, but they may not be valuable to you, so discard them. Whatever they are, if you don't need them anymore. So what are we talking about here? And that's typically the way we typically do things, and we design an architecture or plan around this. So let's say this. Let's say that we have a certain amount of data, and this data is very important. And it's going to be used for the next 30 days. So this is current data. If we're going to use this every day for 30 days, we need to keep this data at easy access. Now, maybe we use this data for 30 days actively, and then maybe for the next year, we may access it, but we may not access it. But we would have access to it. So we move the data to this type of list. So we move the data to a less expensive, but still available. Now we're in the medical industry, so we have to keep our data for 3 years. So what do we do with the data? We typically, once it's no longer useful to us, but we have to have it, we typically keep it in some type of cheap storage, some cheap archival storage. Cloud providers have solutions to this, like AWS Glacier, for example. Everybody has or cold storage with Google. Everybody has an option for this storage. And at the end of 3 years, when we're not legally required to keep it, we trash it. So we do a secure disposal. Okay, secure disposal. All right. What do I mean by secure disposal? So you delete the data on your hard drive. I promise you, there's an application that you can use in many cases to get your data back. Because your data is there, but there's no longer a pointer to your data, but it's still there. Is that deleted? Okay, so I want you to think about it. You deleted data on your personal computer that's sitting inside of your house. It's deleted. For the most part, unless somebody's breaking in your house and stealing your computer, it's not a problem until you give or sell your computer away to somebody else. And when you give your computer away to somebody else, what do? Many of us crypto shred the hard drives. Like we write over it with different data or something like that to make sure that there's no data. Maybe we write all zeros once, and then all ones once, and all zeros once, and one ones. We do it 10 times. And we make sure you can't get to it. Can we do that in the cloud providers' data centers? Can we erase their RAID arrays, erase their object storage, or erase their file storage? No, we can't. So how do we really delete that? How do we make sure that nobody can access that? We crypto shred it. And I'm going to show you what crypto shredding is. So we have our data, and this is what we do. We take this data, then we encrypt it with some freaky kind of encryption, like something, I don't know. So SHA-256 is standard. So let's say we use SHA-512 or something like that. Something really serious, maybe bigger. Now, at this point, we take this data and we encrypt it with something that is super secure. After we've encrypted this data with something super secure, here's what we do. We trash the encryption key. Now, can you get this data that's super heavily encrypted without the encryption key? Nope. So I take this, I encrypt it into something serious, and then I get rid of the key. And then I delete this thing that you can no longer decrypt without the key. So that's called crypto shredding. And that's typically our only option for this kind of data protection in cloud computing because we don't own it. So let's think about backup. You know, many, many years ago, I thought this was absolutely incredible. I saw a company that was incredibly secure. I mean, they had encryption everywhere. They had firewalls everywhere. They had guards everywhere. To work there, you had to be fingerprinted and FBI. I mean, this was a very high security environment. And then they backed up to an unencrypted tape. And I said, all I need to do is steal your tapes. They're like, well, we got a really odd tape drive. I'm like, trust me, we'll figure that one out. And that was the key. So if you're going to take your data and you're going to put it in a backup media, you better find a way to secure that media. So if it's a physical tape, first we want to encrypt the tape, but we also want to make sure the tapes are locked. Where are we sending the tapes? Who's receiving the tapes? Are they going to be stuck outside? Are they going to be brought in? Or are they going to be locked in a secure cabinet? So I want you to think about that in your backup. Now, how do you determine that the data hasn't changed? How do we know that your data hasn't changed along the way? Do we have a tool for that I may have talked about before? Well, it's that hash. Exactly. So let's go back and try to look at this thing along the way. And this is the coolest thing. And if you ever download Linux, if you ever download anything big, I encourage you to check the hash and make sure it's real. So we take our data. So we take the data. Now the data itself is whatever it is. We create a hash of the data, and the data hash looks like this. Well, actually, I wasn't, I had caps lock. All right, well, I'm adding some funny characters here. But this is what the hash looks like. Because every single time, that's not exactly what it looked like, but every single time you put in this data, you get the same hash out. So here's what you do. You put the public hash out there, for example, and when you take the data, you compute a hash, and when you receive the data, when you get the backup, and that's here's your backup, you compare the hash and make sure that this hash and the primary thing, oops, is going to match that same hash with your data along the way. Because we need to know that way that you've got identical backups. Now, if we do digital backups, I'm going to talk about immutable object storage. So we can talk about why that could be cool for our data. So was anybody familiar within the United States, United Healthcare, the largest medical insurance provider in the United States and potentially the world, had a ransomware attack, and all of a sudden the hospitals couldn't authorize surgeries for their patients, and doctors' offices couldn't authorize surgeries for their patients, and half of the US medical world went to a giant standstill because they had no backups of their data and they had ransomware. I mean, seriously, half of the US country went down because a healthcare provider didn't know how to secure their data. So I want you to look at this and consider this for a minute. If I take my data and I back it up to another hard drive and it's on a standard hard drive,
Mike, are you sharing your screen?
So let's say this is my environment, and let's say the data is on a standard hard drive. If there's ransomware sitting on this hard drive, and I back the data up to a different hard drive, is my backup and my primary now infected with the same ransomware? It is. Now, if I put it on immutable object storage, remember, with object storage, we take data. So we have some data. The data gets broken down into an object, and the object cannot be changed. Now the data goes from here to here, and it can't be changed along the way. Is this immutable object storage as a backup concern now for ransomware? It is not, because this can't change on the data that's here. It is write once, read many times. It is immutable. So I wanted you to think about that and really think about how we're protecting the data, how we're protecting the backups. The backup might need to be air gapped, meaning not connected to the internet. So these are the main things that we're going to talk about as it pertains today to deal with data security and application security. I wish we had more time, but we covered the majority of what you would think about from those perspectives. So let me see who has questions.
All right. So that's the end of the content for today.
For today, yes.
Okay. All right. So let's see. We already have some questions that came in. So earlier, they asked but if everything is encrypted, wouldn't that slow the entire system, given that encryption slows down performance?
It depends how it's encrypted. And what I mean by that is encryption is relatively slow if it's done in software. But encryption could also be done in hardware, and encryption in hardware is hugely faster. For those of you that had the same, maybe a Bitcoin mine going on, well, first, you mined it on your CPU and it did a few calculations per second. And then you did it on your GPU and it did a few thousand calculations perspective. And then you switch to an ASIC and all of a sudden you're doing about 45 trillion calculations perspective per second. And the key is it depends on what you're using. So we can use ASICs or these specific application-specific integrated circuits or FPGAs, which are programmable ASICs. They can encrypt at lightning speed. So it doesn't have to slow it down. It just depends on the kind of hardware we use.
All right. Let's see. How do you know if your CSP is using a homomorphic encryption?
Generally speaking, you won't be unless it's a specific instance and you will pay extra for it.
Another one related to the same thing, homomorphic encryption. Is homomorphic encryption connected with public encryption, or are there differences? Now, I know we're going to be
Completely.
going into encryption
Yeah.
in depth in another session, so I
Yeah.
just wanted to keep
Yeah.
that.
So yeah, and I'll cover that much more, but they're completely different. Public key encryption is using certificates and certificate servers and asymmetric encryption for you to access things like a digital signature. This type of encryption we're talking about today. And what was the other one that was in that question, Chris?
So the question was, is homomorphic encryption connected with public key encryption, or are there differences?
They're completely different. Homomorphic encryption is about going from the hard drive to the memory to the CPU while staying in case, whereas public key encryption is more about you verifying the authenticity of a web server with, say, a certificate.
All right. Next one is what's the difference between separation of duties and gap analysis, and when do we apply them?
So a separation of duties is when you make sure nobody does too many things. And you always do that for high security. A gap analysis is when you basically look and say, here's our current architecture, and we need it to be this in the future. So what are the differences between where we are now versus where we need to go for the future? Or if you wanted to become, say, a security architect, and let's say you knew network security, the gap analysis would be, for example, the sales skills, the presentation skills, the executive presence skills, and those other kind of skills that you don't have that you would have to learn. And that's what the gap would be where you're at to where you need to be for your next goal. Good questions.
All right. Next one. Uh, if the underlying server is managed by us, the entire shared responsibility model lands on the user, not the provider.
There is no shared security model. If you own the data center and you own the services, it's all on you. Now, you might be using a hypervisor from VMware, for example, or you might be using cloud software, say Nutanix or from IBM OpenStack. So you'll still have them as a vendor and their vendor patches that you have to deal with. But as a rule, there is no shared responsibility model. You own the infrastructure, you own the servers, you own the network. And because of that, you can get to an extremely deep level of security that you can't do in the cloud provider. And here's the reason why. I can make my own environment very secure, but I can't host an environment for 10,000 people or a million people and make each one security requirements exactly what they need to be. When you go to a hotel, you can't assume you have the security that you would have in a private residence. More ways in, more ways out, public elevators, it's easy to get in. So it's that type of environment we're talking about.
All right. Give me a moment on this next one. It's a long one, so I'm gonna also send it to you if you want to read it off to yourself while I'm reading. Um, so the next one says, when we delete data from our storage, the data isn't completely deleted, which I know is true. My question is, when our storage is full and we delete files, and suddenly space becomes available, where exactly are these deleted files stored before they're permanently removed? And how does the system make the space available so quickly?
So what's really going on is the data didn't go anywhere, but you erased where the data is. So let me kind of show you this as if you were going to think of a hard drive. So if if your hard drive is kind of like this, where you've got, let's say it's all data, 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 and more data, somewhere along the line, if you the data is what has to happen is your operating system and your operating system, it needs to see what's stored and inside of these hard drives that are over here, for example. Let me get rid of that. So we have this data, we have this data, we have this data, we have this data, and we've got more data that's sitting on the hard drive. And what we have is somehow the operating system, and depending upon the storage, like object storage, there's even more of this, but it keeps track of the current data and how to access the data. So when we actually get rid of this, the data is still technically there, but the pointer or the ability that the thing that shows you how to access the data is no longer there. It gets rewritten to something that's zero maybe, but the data is still hidden there. So what you can do is you can use a tool like distro, for example, and where you can go back and you can find and search for that data, and in most cases reconstitute that data because it wasn't deleted. Now, if the data is deleted and what's deleted is the access to the data, but the data is still here, but it's sort of hidden there, but it's still there. And then you write over the data with new data. Now it's going to be a lot harder to get back to the old data because where the data was overwritten with something new. So it's never really gone per se. There's going to be data fragments that are left around. The only way to truly get rid of the data for real is basically to overwrite first to delete it and then to overwrite this with all say zeros. And then once you're done overwriting with zeros, maybe erase it and overwrite it with new zeros, or say ones, and then erase that and overwrite it with zeros, and then say overwrite it at ones. So what you're doing is you're constantly taking the data and rewriting over the data again and again after you deleted the pointer. So at some point, none of the data is supposed to be there. And that's where, like, if you were going to sell your PC, and you might actually have to do several passes where you would delete, 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 and your 4 terabyte magnetic hard drive took 36 hours to shred. That's what was really going over. They were writing over the whole thing, and then they were writing it over it again, and they were writing over it again, and they were writing it over again. So it's still there, but the pointer's not there, which probably isn't that big of a deal in your own data center. But it's a very big deal when it's somebody else's data center, especially if that data was taken. Hope that helps.
All right. So that's all the questions that we've gotten so far. So I'll hand it over to you if you want to wrap it up and let us know what we've got in store for our future sessions.
Absolutely. So, we still have some fun things coming on. We will be talking about what I think is the coolest, which is physical security. We'll be talking to a degree about incident management. We're definitely going to have some fun around cryptography. I mean, I'm not going to get into math level geekiness, although I could appreciate people that can do that. My wife could do it. I couldn't, but I think that stuff's just kind of cool. And then we're also going to talk a little bit about incident management and security operations as we finish out our, fundamentals program. So I've been thrilled to have you here. Now, tomorrow we're going to run a webinar on how to become a security architect. If you're interested, I'd love to join you there. I think tomorrow is a security architect webinar. So if you'd like to join us, it's between 3 and 5 tomorrow. I'm going to talk about what a security architect is, what we actually do as security architects, the actual skills you need, which most people would never know what they are, which is why I run these. And of course, you can ask me any questions. And I'd love to meet you there. For those of you who were here so far for today, great. If you were not here, my team will drop the link to the playlist so you can go back in future dates and go watch the first day and the second day because I don't want you to miss out. Maybe share the word about this free training to others because I really want others to benefit from this. We put a lot of time and effort and money in developing this content, so I want to make sure it's there for people that can help them, especially because it's free. So please do that. I hope to see so many of you in the webinar, and I hope to see others of you in class that I know as soon as possible. And I really just look forward to seeing more of you. So take care, everyone, and I will see you next week or sooner, depending upon how I know you and where I know you from.